ways to describe graphs. The adjacency matrix, and because it's weighted, you see that there's numbers here instead of 0 and 1. We have the adjacency list, where it looks like here they have a hash table with the values, and also an edge list with an extra property of the weights because this is a weighted graph. And you can see the weights as well in the adjacency list. But we've just taken a look at a lot of numbers. I think it's time for us to build our own graph to finalize our understanding. I'll see you in the next one. Bye-bye. Welcome back. It's time to create our own graph. And I've created the template here for you. You can also create your own if you want, but I've only included things that let you focus on the critical part. We have a graph class and a few methods that we're going to have to add. Now, we're going to recreate a graph right here. A undirected, unweighted graph like this using adjacency list. And for the adjacency list, we're going to use a hash table. So how are we going to go about doing this? Well, I have a few things that I've set up for you. One is that in the constructor, we have simply number of nodes that we'll have to increment just to keep track of how many nodes or vertices we have in our graph. And also, I've created the adjacent list for you, which is an object. And as you do this exercise, you're going to realize why we want to use, let's say, an object versus an array. Because if we start removing things from the graph or placing things in the graph that's out of order, it's going to cost us a lot. Remember, arrays on shifting and shifting is expensive. With objects, we can quickly find items and see their connections. So that ideally, in this case where we have 3, or let's look at 0, in this case we'll have 0 is going to be connected to an array of its connections, which will be 1 and 2. So it'll have something like this. Your task is to add a new method called addVertex that adds a new node or a vertex. The naming here kind of goes back and forth. And then also addEdge. That is to add a connection between node 1 and node 2. And keeping in mind that this is undirected, if I could spell, it's an undirected graph. So both node 1 and node 2 point to each other. And if you scroll down here, I've actually created the calls, the function calls that we're going to do. We've created the graph, and then I'm creating 0 all the way through 6, just like we have on the graph here. And then we're going to add the edges, that is the connection between everything. 1 is connected to 0, 0 is connected to 2, 6 is connected to 5. Simply just saying this. I'm never repeating myself. That means I'm never saying add 3 and 1 and then saying add edge 1 and 3. I only say this once, and that's the key. And also the order doesn't matter. If I switch the order of these calls around, it should still give me this graph. All right, I know you're excited to get coding, but the final thing, and this is only optional, if you want to do this yourself, you can also code it yourself, but it's not really that important for this video. I've created a small helper function called showConnections. And you can look through this function if you want. It's not really important to the core of the course, but I've made this so you can check your work. Because if I run this using, at the end, my graph, showConnections, it's going to print out the answer like this. And it's going to show all the connections of the graphs that you've created. And this way you can check that these connections, that is node 4 is connected to 3, 2, and 5. Node 4 is connected to 3, 2, and 5, just like we have here. All right, that's enough for me. Good luck on this exercise, and I'll see you in the solution video. Bye-bye. Welcome back. How did you do in this exercise? Were you successful? Were you not? Here's the thing. This is actually extremely simple, but it looks overly complex. And that's a general trend with graphs. They look really, really intimidating at first and really hard to really think about them in your mind. But once you put things down, understand things, maybe draw things out, they're actually quite simple. And they're very similar to what we've learned up until now. Everything we've learned about hash tables, arrays, trees, linked lists are all part of graphs. And graphs simply use those data structures. For those of you that weren't able to solve this problem, it might be because you were a little bit intimidated as to the task at hand. But let me show you how simple this can be. In order to add a vertex to our adjacency list, all we need to do is to simply say this.add, or this adjacency list is going to have node. So we're adding the key into this object of the node that we want to add, and that's going to equal an empty array. Because when we enter a new node, it's not going to have any connections initially. We want to add the edges afterwards. And then finally, we want to increase the number of nodes by 1. Now we have one more. That's it. We've just created our nodes. Look at that. We have 0 all the way through 6, and they are in our graph. Unfortunately, none of them connect to anything. We've just created the nodes, but none of the edges. So let's go ahead and do that. With the edges, because this is an undirected graph, what we'll have to do is say this dot adjacent list is going to say node 1, that is the first node that we're giving. And the node 1 is going to push. Remember, this is an object, so we're getting the key. So that is, let's say this is node 0. It's going to push to the array of connections that node 0 has and say that it's going to be connected to node 2. And because this is undirected, that means we have to do it the other way around as well. So we simply copy this. Let's make this a little bit bigger so you can see. And we simply reverse things. So node 2 is also connected to node 1. If I press run here, look at that. We have our graph. How simple was that? That wasn't bad, right? And I mean, we could create this in a linked list if we wanted to, but the concept is the same. If we look at 0, that is connected to 1 and 2, we can confirm that 0 is connected to 1 and 2. If we look at 1, 3, 2, 0, 1 is connected to 3, 2, 0. And let's check maybe 5, which is connected to 4, 6. 5 is connected to 4, 6. And there it is. We've just created our very first graph. When it comes to interviews, graphs aren't as big of a topic as the other data structures, mostly because they take a bit of time. And questions regarding graphs can be overly complex. That doesn't mean that you won't see them, but they are rare. However, by knowing the basic fundamentals, what types of graphs we have, and how you might create graphs, how you might want to hold data in graphs, such as adjacency matrix, adjacency list, and edge list, you already show that you have the ability to understand graphs, which is an advanced concept. Now, because graph questions aren't that big a part of interviews, we won't be spending any more coding time on it. But also keep in mind that we have a section coming up on algorithms where we're going to dive a little bit deeper into things such as breadth first search and depth first search, which can be applied both to graphs and trees. So if you feel like you can still learn a bit about graphs, don't worry, we're still getting there. But for now, congratulations on creating your first graph. I'll see you in the next video. Bye-bye. Welcome back. What are the pros and cons of graphs? Well, when it comes to performance and big O, it gets a little bit complicated because there are so many different types of graphs. You can think of graphs as really useful when it comes to relationships. They're simply indispensable because some data just needs to be in a graph form. There's no other way around it. And there are algorithms around graphs, such as the ones that we're going to be talking about in the algorithms section, that allows us to perform operations, such as finding the shortest path or traversing a graph. But when it comes to graphs, because they can get complicated, scaling is pretty hard. You need a big company, or at least a lot of resources and engineering power to make sure that you build graph data structures that scale well. But luckily for us, you usually will never have to implement your own graph in production, or at least for 99% of the population. There are tools like Neo4j, which is a popular database that allows you to build really fast graph databases. And most of the time, you'll use tools like this to build complex structures to contain our data. Congratulations! We've now covered another part of our data structure mind map. That is graphs. We learned about cyclic, acyclic, weighted, unweighted, directed or undirected. We were also able to build our own graph. Now there's still a few things left that I see up there and perhaps over here, which we're going to get into in the algorithm section. But for now, take a break, drink some coffee or tea, and I'll see you in the next video. Bye-bye. There we have it, our end to the data structures section. Was it as scary as you initially thought? Hopefully, by the end of this section, if you've watched all the videos and done all the exercises, you feel a lot more comfortable. You can use the tools that you've learned to be a better engineer and make better decisions. Hopefully, you don't look as scared as this emoji did at the beginning of this section. And we've learned that these data structures, at the end of the day, are our friends. And by the way, I'm really proud of this slide. I spent way too long creating this little thing that I have. I have Mr. Hash Table here. That's Mrs. Array. That's the little linked list. That's Mr. Q, Mrs. Stacks, scary looking graph, and of course, Professor Tree. Anyway, I hope you're no longer intimidated by these subjects, because all around us, when we look at technology, they're all built by data structures. We hold information in data structures. No matter how many data structures there are and there will be in the future, most of the building blocks are right here. You see, something like blockchain that has become really popular in recent years are just data structures that we've learned about. It has some aspects of linked lists. It has some hashing that it does, which we know about. And it also uses some trie data structure and trees. Having the fundamentals that you have now, one day, maybe you'll build your own data structure. I'll see you in the next one. Bye-bye. There we have it. We've just completed our data structure section. We went through all these data structures, even some sub-data structures. And you know what? We've completed a lot of this mind map. We've talked about arrays. We've talked about stacks and queues. We've talked about hash tables, linked lists, trees, and all the types of trees that we have. We even talked about graphs. All these little boxes that are data structures, we now have an understanding of what they are and how they are used. But there's a few other pieces of this mind map that we need to go through, and that is algorithms. And you'll see algorithms depicted here in rocket ships. Our last piece of the puzzle. But you might still have a few questions that haven't been answered. And there are some things that I left out because they apply more to algorithms. When it comes to sorting, we're going to use arrays and trees. When it comes to dynamic programming, we're going to be talking about hash tables. When we talk about breadth first search and depth first search, that's used in graphs and trees. Recursion, well, that comes up a lot in trees as well. So Now that we have our fundamentals for data structures, we're now ready to talk about these algorithms that come up a lot in interviews. Because we now understand how data structures work, we're able to talk about algorithms intelligently and understand them at a fundamental level. I'll see you in the algorithm section. Bye-bye. Welcome to the algorithms section. This is a word that immediately just sounds nice, right? All the companies are using it these days to sound like they're doing something really, really important. Everybody has a secret algorithm that they use to make machine learning models, analyze user data, make companies lots of money. But underneath the hood, algorithms are just functions that programmers write. A 2-line function is technically an algorithm. A 1,000-line algorithm that sorts through images is also an algorithm. Algorithms are simply steps in a process that we take to perform a desired action with computers. If we go to Wikipedia and search list of algorithms, the list is pretty endless. There are a lot of algorithms. It's impossible to know all of them. You can create your own algorithms, you can use other algorithms that are popular and well established. But let's get back to our question of what are algorithms. If we combine our knowledge of data structures, the ones that we worked on in the previous sections, algorithms allow us to use language built in data structures like arrays and objects, or primitives such as integers and booleans, and even custom data types like we did when we used the class keyword to create stacks, queues, binary search trees. Well, algorithms allow us to use these data structures to perform actions on that data. Remember this, right? Data structures and algorithms create programs. In this course, we're going to talk about the most common interview algorithms. So that long list on Wikipedia won't be as intimidating because we're only going to focus on the ones that matter, especially for interviews, but also the ones that matter most in your career. Specifically, we're going to go over these topics when it comes to algorithms. Now, why are these algorithms so common in interviews and especially in big companies? Well, you can get away with not knowing these topics for a long time as a programmer. But as we have learned, Big O and scalability of code is important as companies get larger and larger. By learning these listed algorithms, we're able to do majority of the scaling we need to improve our programs. Remember our Big O cheat sheet? And how we haven't really talked about O log n and On log n? Maybe a little bit in the previous videos? Certain algorithms allow us to simplify our Big O complexity into smaller or better time complexity. So that by using the right algorithm, I could take a function that has a Big O of this notation down to something of On log n, or something that has a linear time complexity to O log of n. And these are used everywhere in large companies because large companies handle lots of inputs, lots of data. So this topic is extremely important to them. And as your career grows and grows, these topics will be more and more important to you. So let's dive in to our first topic. I'll see you in the next one. Bye-bye. Okay. I'm actually starting with a bit of a trick here. Recursion, which we're going to talk about in the next couple of videos, isn't technically an algorithm. It's more of a concept that we're going to use throughout this section of the course to write some really interesting algorithms. When we get into sorting and searching through a binary search tree, we're going to be using recursion a lot, so I want to prepare you. And obviously, it's also a common topic in interviews. Actually, this is one of the most popular topics, I would say, when it comes to interviewing. Now, What is recursion, really? When you're searching for files on a computer, for example, if you're on your desktop and you want to find all your music files, your MP3 files on your computer, you can't do it by just looking at one folder. You want to look at folders recursively to find all your music. Let me show you what I mean. I have the project here that we've used for one of my other courses, and it's a backend API in Docker. Now I've cloned this repository and I have it right here on my desktop. Now, if I wanted to search through all the files in this project, I can simply type in ls to show me the files. But as you see in blue here, we also have folders that inside of them also have files. How can I also see the files in this folder? Well, I can do something called ls-r. And R, guess what? Stands for recursively. If I do this and I press enter, look at that. I get also the files inside of the folders. You see that I have a controllers folder with JavaScript files. I have Postgres folder with some Docker files, some SQL files. And within those, I also have another folder that has different files. But because I was able to list items recursively, my computer went inside of each folder and printed out the files. So what is recursion? Well, recursion is when you define something in terms of itself. Simply, it's a function that refers to itself inside of the function. All right, there's no way you got that right. That's probably the most confusing definition ever. Again, let me show you an example. If I open up the console here, a recursive function is a function that refers to itself. So I can create a function called, let's say, inception. And this function is recursive if I refer to itself inside of it. Oops, let's try that again. If I say inception here. This is a recursive function because when this function runs, it's going to call itself and run again. The problem with recursion and why people find it so difficult is that it's an intimidating topic when people start talking about math and theoretical applications. Instead, let's focus here on how recursion helps us solve problems. Recursion is really good for tasks that have repeated subtasks to do. That's it. Kind of like when we looked at the folders inside of this project. And the reason recursion is so important, and the reason that I talk about it first in this section before we dive into all the other algorithms, is that this concept is going to be used in searching and sorting algorithms that we're going to be talking about. For example, traversing a tree, if you think about it, are simply same tasks that we do over and over again. Remember when we build our own tree data structure, our binary search tree? And I gave for you a little function at the end called traverse that allowed us to print our tree so we can verify our answer. If we look at this closer, we see that we're using recursion here. I have a traverse function that calls itself within here. And this is something that we're going to demonstrate a lot of when we talk about searching and sorting in the upcoming sections. Recursion is everywhere. When we do DOM traversal on a website, if we go to elements here, when we do this traversal on an HTML document object model, we're using recursion. In JavaScript, when we have nested objects, so an object inside of an object, well, we use recursion. But the key to getting recursion is to understand that it's not that complex as long as you practice it a little bit. Once you get it and get over the initial hump, then it becomes second nature. And my goal is by the end of these videos that you're going to get recursions. So let's get started. I'll see you in the next one. Bye-bye. Welcome back. I'm about to show you my favorite animation of the course. I'm very proud of it, so don't laugh at me if you think it's silly. I like to think of recursion as this scenario, where you have this tap pouring water into a glass for this little man that's sitting on the couch watching TV. And when I think about recursion, I like to think that they have two big problems. One is that, well, they're kind of difficult to understand at first. The second is that we can have a case like this, where I'm pouring water into a glass, I'm pouring water into a glass, I'm pouring water into a glass, and that is me calling the function over and over and over. And as we keep going, fills up the cup past its limit, it keeps going, it doesn't stop, it keeps calling the function until, oh boy, the man has drowned. What just happened here? This is called Stack Overflow. Let's go back to some code. Remember the function inception that we created? If I run this function and I say inception and simply run this function, I'll get an error. Let's make this a little bit bigger to see. I get an error saying maximum call stack size exceeded. My browser, in this case Google Chrome, is smart enough to say, all right, you got to stop this madness. I'm just calling this inception function over and over and over and over. Because remember, our function just calls itself. And eventually, if Google Chrome doesn't stop this, it's going to crash. And in the past, that's what would happen. If I run this function, the browser would crash and I would have to restart it. But they've added a safeguard here saying, hey, you've called the maximum call stack size. You got to stop what you're doing. Now, this is called Stack Overflow. Why is that? Let's dive deeper into this topic. Just going to clear the console here and write our inception function. But this time, I'm going to add a keyword called debugger that the Chrome browser is going to detect and pause the function when it sees this word. So I'm going to run this function. And you'll notice that as soon as I hit enter, it's going to stop and give me a little panel here where I can control the function. Let's hit enter. And there you go. I'm in now the debugger mode. And you'll see here a few things. One, it'll show me where I am in the function. And also show me, let's change these around just so it's a little bit cleaner. I'm going to make this a little smaller. There you go. You see here something called the call stack. Now from the name Stack Overflow, this might give you a bit of a hint. Right now, we've called the inception function right here. We haven't called it the second time around. If I click on the step over icon over here, it's going to go to the next line of the code. It's going to go to the next, and now it's going to call the next inception function. Have a look over here at the call stack as to what's going to happen next. Did you see that? I just added another function on the call stack. And as we know about stack data structure, we're just adding the function call on top of the older one. And if I step over here and go again, that's a third function call. And if I keep going, you'll see that I'm just adding more and more and more things to the stack. But there's a problem here, right? Nothing's getting popped from the stack. Instead, the function just keeps running until we run out of memory here. Remember, stack, in this case, is grabbing a piece of memory from our computer and adding inception to the stack. And as you know, memory is limited. We don't have infinite amount. So as we keep going, it's going to stack overflow and throw an error. And this is one of the biggest problems with recursion that we're going to get into later on. As you see here, though, it can be very, very dangerous because we can run programs that overflow, that never stop, that have infinite loops, essentially, that crash our programs. You'll also see here that this costs memory. A stack is holding these function calls. And recursion, one of its downside is that we have to hold on to these calls and remember them one by one, which can get really expensive. So if you ever get asked this question in an interview about recursion, maybe a possible problem with recursion, you can simply say, well, the computer needs to allocate memory to remember things. Stack Overflow can occur when we have recursion and there's no way to stop this recursive call. It's simply the computer saying, whoa. Okay, this is getting silly. I'm not remembering any more things. I'm out of memory. I am going to just error out. In the next video, we're going to try and solve this problem and learn about something called a base case, a thing that you have to have in a recursive function to stop it from doing this. I'll see you in the next one. Bye-bye. Every recursive function needs to have something called a base case or a stop point. Remember my example at the beginning where I showed you how to recursively check out all the folders in one of our projects? We have to tell the program, hey, if the subfolder we're going to no longer has any more folders, stop. If this stop wasn't there, the function would just keep running. So recursive functions have two paths. One is the recursive case, that is, call the function again and run it. And then the base case, that is, stop calling the function, there's nothing more to search. So how can we add this feature of telling the function, hey, quit it. You're being ridiculous right now. You need to stop. Well, we can do something like this. We can create a counter, and we'll say this counter is 0. And we can add a conditional statement. We'll say that if counter is greater than 3, in that case, just return done. Otherwise, we'll call inception, but we also want to increment the counter by 1. So if I click run here, well, I have to call the function first. Let's say inception. If I call this function right now, what do you think will happen? Pause the video, think about it, because I'm about to click run in 3, 2, 1. I get undefined. Is that what you expected? Just to show you something, if I comment this code out and we just do this inception, where we just keep calling inception, and perhaps do a console.log here saying hello, and I click run, I get maximum call stack size exceeded. Okay, we know by looking at this function, this version of the function, that it's never going to get to console.log because as soon as it hits the first line of the function, it's going to go back and say, oh, I'm calling this. And then it's going to go here. It's just going to bounce back and forth, never getting to console.log. But if we go back to what we had before, well, our function clearly has ended. It hasn't done Stack Overflow. And at one point, it's ended because we increment the counter. So let me console.log here our counter and make sure that this works. If I click run, I get 0, 1, 2, 3, 4. When it gets to 4, counter is greater than 3, so we're returning done. But why is there no done here? And this is a great illustration of how recursion works. I'm going to copy this code and go back to our browser over here. Let me refresh this page to make sure that we have a clear global variable. And I'm going to copy and paste inception. This time around, I'm going to add the debugger keyword so that we can debug our code and go step by step through it. Let's run Inception and see what happens. All right, we're back to our debugger. We see that we have the call stack here. Inception has just been called by me. And I also opened up this little tab called Scope. For our case, we want to just open up the script scope. It shows us what variables we have available to us. In this case, we have counter, which is 0. So I'm going to click Step Over, and it's going to say, hey, we have counter is equal to 0. Is that greater than 3? Nope. I'm going to skip over, increment counter, and run Inception. We see that that happened. Counter has now been incremented because we've gone through this line, and now we go to Inception. We're going to run the function again. And you'll notice that the call stack, when I click this, it's going to increase. Perfect. And we're going to go one more time. Counter is now 1. Nope. Don't return anything yet. Increment the counter. You'll see counter goes to 2. And we're going to run Inception again. And we keep going once more. Passing through. Counter becomes 3. Adding Inception to the stack. And then one more time. 3 is not greater than 3. So we go one more time. Calling Inception. Adding it to the stack. We now have these many stacks. Counter is at 4. And then we step over here. Counter is now 4, which is greater than 3. We're finally going to enter the if condition. That's going to return done for us. Let's see what happens here. I'm going to click Next. And I click Next again. Look at that. We have a local variable now that has return value done. We've now returned done, and we're no longer going to call Inception. The call stack is now going to start popping off these functions because it's going to say, oh, we have a return keyword. I'm going to stop whatever I'm doing at the bottom here and return from this function. So this Inception function is going to get return done. But notice what happens next. Oh, I get return value undefined as we popped off the top item from Inception, from the call stack. And if I keep popping things from the call stack, the return value is undefined, and that's what we get. Now, why is that? Well, if we go back to our function, what you just saw was us essentially doing this. We called Inception once, twice, 3 times, and then 4 times. And within here, when we finally got here, we said, oh, return done. So this Inception function turns into done. And then we go to this function. Now, the problem with this, and I know this can get confusing, is that once we've returned once, we've popped off the stack and we're now at this part of Inception. But this Inception never returns anything. When a function doesn't return anything, it just returns undefined. So we need to keep telling it to return this done and bubble it up towards the very end. And this is something that you have to keep in mind with recursion. There's usually a base case, and you always want to make sure you return so that the value that you want gets bubbled up all the way to the top. In our case, all we need to do is say return Inception. This way, this Inception knows to return whatever its result was, which was done. And this Inception knows to return whatever this result was, which again is done. And so on and so forth until we get done back. Let's run this again. And I have to call the function. Let's do that again. Inception. And run. And we're done. Very, very nice. If I go back here and go back to the console, I encourage you to try this out, this time adding the return keyword to inception and running through the debugger to see what happens. But what I just showed you is all you need to build recursive functions. You have 3 rules. 1 is to identify the base case. 2 is to identify the recursive case. So we've identified the base case, when to stop, the recursive case, that is when counter is less than 3. And then finally, our third step is to get closer and closer and return when needed. And that usually you have 2 returns for the base case and the recursive case, because you want to return something at the end of the function. So let's comment this out. We have an idea of how recursion works. The function simply gets closer and closer and closer to the base case, and once it gets to the base case, it finally returns and pops functions off the stack. But that's enough talking from me. I think it's time for us to do some coding exercises to get really familiar with this topic. I'll see you in the next one. Bye-bye. Welcome back. I have a fun little exercise for you. And now you're asking yourself, Andre, you say all exercises are fun. You're a big liar. All right, fair point, but I think this one's going to be fun, so stick with me. I want you to write a function, actually 2 functions, that finds the factorial of any number. Now, why 2 functions? Well, one function is going to be recursive, using what we just learned, where we have to create a base case. We have to follow the steps, right? If we go back, we have to identify a base case and a recursive case. And then finally, make sure that we return both cases. So this recursive function is going to return an answer. But what is a factorial? A good way to think about factorial is this notation, 5 exclamation mark. Factorial simply means multiply 5 times 4 times 3 times 2 times 1. You keep going down one by one, multiplying each number until you get to 1. So 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1. And you'll notice here that it's a recursion pattern that we're doing. We call the function and we have 2 cases that can happen. We have the base case to stop or recursive case, and so on and so forth. And we keep going until we hit 1. So I want you to build a function that does this for us. I'm going to write the function factorial. You're going to put in 5, and it's going to run through this. But remember our definition of recursion. Recursion is when you define something in terms of itself. Now, a good way to think about factorial is this. 5 factorial is simply 5 times 4 factorial. You see over here, 5 times 4 factorial is factorial 5. 5 times 4 times 3 factorial, 4 times 3 is 5 factorial, because 4 times factorial 3 equals factorial 4. And you see here how we might have a recursion function that we can write. Using this knowledge, see if you can create a function that allows you to do this. Now, when it comes to this question, there's 2 ways that you can go about it. You can do the recursive approach, where the function calls itself, or you can do the iterative approach, which means looping. And most of you are probably going to find it easier to solve it with this way, with just a for loop, for example. I'm going to leave this up to you to figure out. See if you can do both functions. and see if they give you the right number. And in the next video, I'll show you the answer. I'll see you in that one. Good luck. Welcome back. Let's start off with the iterative approach. That is, no recursion. If we want to run the function, let's say find factorial iterative 5, well, we can create a variable, let's say answer. And for now, this answer will be 1. And all we're going to do is do a for loop. We'll say let I equals 0. Or, in our case, to simplify things, let's start at 2. And I'm going to explain in a second why we want to start at 2. I'm going to say I is less than the number, and then we're going to increment I by 1. Now, why are we starting at 2? You might notice a shortcut here. 1 factorial is just 1. 2 factorial is 2 times 1, which is just 2. So these last 2 bits, if somebody says 1 factorial or 2 factorial, we can just simply return the number that they've entered because there's no real calculation that we need to do. So this is a little shortcut so we avoid extra loops by just saying that if the number that the user enters is, let's say, 2, so that is 2 is not greater than number 2. The way we have it now, if somebody enters find factorial iterative 2, we're going to return 1. But instead, we can just say maybe a simple conditional check saying that if number equals to 2, we'll just say that answer equals to 2. So that if I run this function and just say 2, I get 2. If I say 1, I get 1. And there's other checks that we can do, obviously. But for our case, this is good enough. Let's look at what we can do inside of here. Well, the way factorial works is to simply say answer is going to equal answer times I. So that if I click run here and let's do 5, I get 24, which is actually not the right answer because 5 times 4 is 20 times 3 is, well, clearly higher than 24. And that's because of a little mistake here. We want to make sure that this is equals because we want to include the number 5. So if I run this again, I get 120, which is the right answer. 5 times 4 is 20 times 3 is 60 times 2 is 120 times 1 is just 120. Perfect. So hopefully you got that answer correct. What about the recursive approach? In the recursive version, we'll just do a simple check saying if number is equal to 2, and we can do other checks as well, but that should be enough for now for us to create a base case. So if the number gets to 2, we'll just return 2. There's our base case. That's how we stop. Next, we're going to return our recursive version, which will simply be number times the function. And in this function, we're just going to say number minus 1. And that's the key here. We want to always get lower and lower until we hit the base case. So if I hit run here, let's do recursive this time. I'm going to move this up over here. And if I hit run, I also get 120. And this is a little hard to wrap your mind around. So you might want to copy this code and open up Google Chrome Developer Tools like I showed you and go step by step But if we start with the number 5 here, well, does 5 equal 2? Nope. Then we'll say 5 times, find factorial 4 should be our answer, just like the diagram that I showed you. And we keep going until we hit the base case of does the number equal 2? Now, one last bit. What do you think the time complexity of these two functions are? Well, one uses a for loop, with the loop being the number associated with it. And we're doing a bit of a shortcut here, so it's technically less than O of n, but because of our big O rules, this is still going to be O of n. The recursive function, if we look at this, we are looping how many times? Well, we're calling the function find factorial recursive the same number of times as the number itself. So this also becomes O of n. If you got this question, good job. It's a tough one. If you didn't, don't worry. We have another one coming up. I'll see you in the next one. Bye-bye. Welcome back. You can't talk about recursion without talking about the Fibonacci sequence. What is the Fibonacci sequence? Well, it's this sequence right here. The pattern, if you notice, is that we're always adding the first two items equals this one. So 0 plus 1 equals 1, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, so on and so forth, so on and so forth. So the previous two numbers always equals the current number. So I have another exercise for you. This one a little bit tougher than the previous one. Given a number n that the function is going to receive, return the index value of the Fibonacci sequence. So if I say that I want the n to equal 2, it's going to give me 0, 1, 2. That is the number 1. This function is going to return 1. If I say Fibonacci number 8, I would get 0, 1, 2, 3, 4, 5, 6, 7, 8. I would get 21. The function will tell me what number is associated with the index that I give it. Once again, I have the iterative approach, that is using just simple for loops, and also the recursive approach. I challenge you to try both of these and see if you can do it. And a big hint here is that the recursive approach is actually easier than the iterative approach. So good luck out there, and I'll see you in the solution video. Bye-bye. Welcome back. How was that exercise? Does your brain hurt from all this confusing sequence? Let's actually start off with the recursive function this time. Because in this case, the recursive function is actually a lot simpler to think about. All we would do with our recursive function is to say, well, the base case is going to say number, or n, is going to equal 2. If that's the case, simply return. Actually, if we look at the sequence, we see that if the index is 0, the answer is 0. If the index is 1, the answer is 1. And if the index is 2, then the answer changes to 1. So instead, our base case can maybe just simply be if n is less than 2, we're always going to just return whatever the n is. So if we say 0, it's going to return 0. If we say 1, it's going to return 1. If we have an index higher than that, well, then we have to do some recursion. And all we're going to do here is have another return statement and say this function, I know that this function is really, really long, we can probably make it shorter to just say fib. And I noticed that we don't need the iterative here. That will make it a little shorter. There you go. Now all we're going to say is fib is going to equal n minus 1 plus the same thing, n minus 2. Because remember, the sum is always, the answer is always the numbers 1 and 2 before it. So we're just adding the numbers 1 and 2 before our sequence. And that's it. If we run this function, let's say Fibonacci recursive of 3, and I click run, I get 2 because 0, 1, 2, 3 is 2. Let's do 8, which should give us 21. And I click run, or give 8, I get 21. Nice. And if I do 0, I get 0. If I do 1, I get 1. If I do 2, I should get 1 right here. Nice and simple. Well, I don't know about simple, right? You really have to get comfortable with this before you truly understand what's happening. But I have a little diagram to help you here. All we've done is simply this. If I added 7 here, our recursive function is going to get 1 less than 7 and 2 less than 5. And then within those functions, do the same thing. 1 less than 6, 2 less than 6. 1 less than 5, 2 less than 3. And it's doing all of these, all of these, all of these, until we get to fib of 1, 2, where we have our base case that returns that number. So this becomes 1. This also becomes 1, and then it keeps going, keeps returning until we get to fib of 7. Now this is a diagram that we're going to get back to, but you see we're doing a lot of calculations here. But simply put, this is all we're doing. Now I said that the recursive approach is actually simpler than the iterative approach. Let's have a look at what the iterative approach would look like. We'll create an array, and there's many ways of doing this. This is my preferred way. And this array is going to have the initial items of the sequence, 0 and 1. And this is going to, first of all, return the array and item of n. We're creating this array and then grabbing whatever index the user wants. In our case, if the user requests 0 or 1, we already have the array pre-filled with 0 and 1, and it's going to return the same. But we still need to calculate for all the other ones. That's where we do a for loop and say let I equal 2, because we're going to start adding when the index is 0, 1, 2 to start filling this array. We'll say I is less than n plus 1, or we can do equals here if we want. We'll leave it at that for now, and we'll increment I++. And in this loop, we're going to keep going until we hit the number of index that we're interested in, and all we're going to say is array.push array I minus 2 plus array I minus 1. Similar to what we did before, we're just summing the previous two numbers and pushing it to the array. All right, now let's see if this works. I'm going to comment out this one and just do the iterative approach. I get 2 for 3. What about index of 8? I get 21. Perfect. And then if I do index of 0, index of 1, and index of 2, should be 1. Perfect. Now, I said that the recursive approach is simpler than the iterative approach. Now, that's my personal opinion. You might not think that. You might think that this was quite easy. But to me, this reads a lot nicer than all this thing that we're doing. And this is something we're going to get into in the next video, where we talk about the trade-offs between the iterative and the recursive approaches to these problems. And why, maybe you're wondering right now, why would we ever write anything recursive if you find this confusing? We'll get to that. But the one thing I want to show you is something that we just learned here that is new to us. What do you think the big O of these two functions are? Well, in our iterative solution, the big O is linear time, right? It's O of n. Basically, we're just iterating through the loop n minus 2 times because we're skipping the first 2 items, which in turn makes it O of n. But what about the recursive approach? Remember the diagram I showed you? That's a lot more calculations than just the 7, right? We have a lot of function calls that happen. In this case, in the recursion solution, it takes what we call exponential time. The size of the tree exponentially grows when n increases. If Fibonacci number was 8, we would have this tree as well as another tree underneath the fib of 8. So what is the big O of that? This is very exciting because we're learning about a new big O notation. We're learning about this one, exponential time, which can be seen with recursive algorithms that solve a problem of size n, 2 to the power of n. If we go to our big O cheat sheet, this is O 2 to the power of n. You see how much it increases? That's pretty bad. It's bigger than even O of n squared, the 2 nested for loops. Exponential time means every additional element in the Fibonacci sequence, we get an increase in function calls exponentially. And here's a fun little trick. Although this is O of n, the iterative approach, this function, because it's O of 2 to the power of n, if I run this function, let's say if we do 10, I get a result. If I do 15, I still get a result. What if I do 20 here? All right, it's starting to get bigger and bigger. If I do 30, if I do 40, do you see how much longer that took to calculate? Because our time complexity is increasing more and more. If I do 43 now, you'll see that we're waiting and waiting and waiting for the calculation to happen, and eventually the browser comes up with the calculation. As a bonus question, think about how many calculations Fibonacci 43 required. This, although might be more readable, is not an ideal solution. As you can see, big O time complexity is pretty big. And this is something that you might get asked in an interview. And I know what you're thinking. Andre, you just taught us about recursion and it's not even good. It's slow, it's confusing. Why would I ever want to use recursion? In the next video, I'm going to talk about this trade-off. Why would you ever use recursion over something that is iterative? Why would any sane person do that? And as you'll find out, there are some pros and cons. And as a matter of fact, a function like this, such as Fibonacci sequence and recursion, can be made to O of n using something like dynamic programming and memoization, which we're going to talk about towards the end of this course. And we're going to get back to this. But let's finally answer the question in the next video. Why would you ever use recursion over something iterative? I'll see you in the next one. Bye-bye. Welcome back. There is a theorem that states anything that can be implemented recursively can be implemented iteratively. That is, you can go your whole life without implementing recursive functions and just use loops. Okay, so why would we ever want to confuse ourselves with a topic like recursion that can be a little confusing? Well, for some problems, it's actually easier to write, but it really depends on the situation. Keep in mind that there's always two options. And by now, you know that with programming, there's always pros and cons. And a good engineer is somebody who can make the right decisions based on those pros and cons. But I want you to keep this in mind for interviews, because interviewers will ask you to solve a problem. And a problem that can be solved with recursion can usually be solved iteratively as well. And looking at our Fibonacci function, this is a simpler example of recursion. But there are times when recursion can keep your code dry. That is, do not repeat yourself. A big rule when it comes to programming. And there are a lot of problems when it comes to recursion as they get harder and harder when using recursive functions allow your code to be more readable and also dry, simpler, have less loops happening with confusing code. And I'm a little bit biased because although recursion is a powerful technique, in my opinion, it's not always the best approach. So you need to make sure because of, or its main drawback. That is, although recursion can keep your code dry and make your code more readable, it also creates this extra memory footprint. Because every time we add a function to the call stack, it adds extra piece of memory. So you have cases where you can get stack overflows. Or if your system has expensive memory, you want to avoid making too many recursive calls. And for some people, recursion is also something that is hard to wrap their mind around. And if you have a team of young engineers, of developers that aren't familiar with recursion, that may not be the best option. But the main drawback is this, that iterative approaches tend to be more efficient because they don't make these additional function calls that take up the stack space, with the downside being that iterative solutions might be not as readable. And the rule that I like to follow is that I like to use recursion when you're working with data structures that you're not really sure how deep they are, where you don't know how many loops to go through. And as you'll see, recursion is really useful for things such as tree data structures and doing traversal because that is often the case. Now, in the next video, I want to talk about this topic a little bit deeper and when to use recursion. But I do want to point one thing quickly. There's something called tail call optimization in many languages. And for example, in JavaScript with ES6, it allows recursions to be called without increasing the call stack. You can read more about it in the resources that I'll provide to you in this video. But in other languages as well, there are certain ways to write recursions so they're more memory efficient. So this large stack issue can actually be resolved during production. But let's talk about a definitive guide to when to use recursion in the next video. When should we use recursion? This is the rule that I like to use. When it gets to complicated problems like traversing or searching through trees or graphs, something that we're going to talk about with breadth first search and depth first search, recursion is really, really useful and better than iterative approaches. And with sorting through items, there's also cases that we'll see that recursion is preferred. And when it comes to recursion, these are the rules that I like to follow. Every time we're using a tree or converting something into a tree, consider recursion. And there's 3 key things in an interview question that might trigger a recursive solution. One is that a problem can be divided into a number of subproblems that are smaller instances of that same problem, such as the exercises we've done with Fibonacci numbers or factorial. We can break those down into little trees that break down to smaller and smaller pieces. Those are inherently recursive problems. Another factor is that each of these instances of subproblem is identical in nature. That is, the calculations that we need to do are pretty much the same. They may be smaller values, but the actual calculations underneath it is all the same over and over and over. And then finally, the third point is that those solutions, if you solve the smaller problems, the leaf nodes of that tree, and you combine them, that solves the problem at hand, then that is a recursive solution that you can use. And you'll see a lot of divide and conquer using recursion. Remember divide and conquer, which we mentioned when we got to the tree data structure lessons. It's kind of like looking through a phone book. When you're looking for Bill in the phone book, you're not going to start from A and simply go one page at a time from left to right. No, you usually split the phone book in the middle or try to go to the B section of the phone book and start dividing up the problem page by page until you get closer and closer. This divide and conquer type of questions usually have recursion in them. And as we know, the one thing that recursions can do that looping can't is that they can make tasks super easy, such as these types of problems. As a matter of fact, I encourage you to write your own traverse function that we used in our tree data structure. This is something that we're going to get to when we get to searching in the algorithm section. But if you want to challenge yourself, see if you can write a traverse function like I did over here using recursion. And then also try to write it with loops. You'll see that with loops, things like tree traversal is a headache. I can't even do it from the top of my head. With recursion, it's pretty straightforward. With loops, you usually have to maintain some sort of a stack to keep track of things, and it really adds a lot of complexity. So use the rules below to notice when a recursive problem presents itself during an interview. I'll leave a few more exercises for you after this video. But as we'll see, we'll come back to this topic when we get into other algorithm sections. And things will start to get clearer and clearer. I'll see you in the next one. Bye-bye. When we talk about recursion in computer science, we're talking about a function that calls itself. This type of technique is really good at some problems because of its ability to maintain state at different level of recursions. Just like our couchman watching TV here, recursion can be thought of as a bit of glass that gets filled up with recursive calls of functions, and then we start popping from the top until the very last function gets popped off and returns a value. One thing that we want to be careful of with recursion was this idea of stack overflow, this added memory space, as we keep calling the same function over and over until we possibly can reach a limit and get stack overflow. The rule of thumb that we learned is that we should use recursion when it makes code more readable. But sometimes it can be less efficient than iterative or looping solutions, so we have to be careful. We also learned the rule that anything you do with a recursion can be done iteratively. And in interviews, you'll get asked the question of the pros and cons of why we might want to use recursive over iterative. And I know I've brought this up before, but it's worth repeating. Recursion is interesting and clever, but can be costly, so you have to be really careful with it. because recursion and space complexity are not friends. But when it comes to some problems like sorting and tree traversal, you'll see that we're going to have to use recursive solutions to make things simpler. Specifically, when we talk about these upcoming topics, we're going to be using recursion. So get ready for it. Merge sort, quick sort, tree traversal, graph traversal, all use recursion. Now we're equipped a lot better to handle those situations that are going to come up. We're starting to build our mind map slowly and slowly. And you see over here that when it comes to tree data structure, ask yourself, should we use recursion? Most of the time, you do want to use recursion, but be mindful that space complexity or stack overflow can happen. I'll see you in the next one. Bye-bye. Hello, and welcome to the next part of the algorithm section. Yes, I'm still excited despite the next topic, which is probably my least favorite. You see, in the past, when I learned about sorting, it involved a lot of math, a lot of different algorithms, and I just never really enjoyed it because I didn't understand why we needed to know sorting. I mean, you just have a sort function usually in a programming language, and that's it, right? I just never understood the point of it. And you're probably thinking the same thing. All right, Andre, there's nothing to learn here. I'm going to skip over these sections. Great lesson. See you later, right? Well, not really. Let me explain. In an interview, sorting is really important. You hear questions like, take an array of numbers and sort them, or the interviewer wants you to do something to some input, and they tell you that this input is sorted. And you're wondering, why did they just tell us that? Why does it matter if it's sorted or not? And why do companies care so much about sorting if I can just use the built-in sort method in my own language? Well, here's the thing. Sorting is not a big deal when it comes to small input data. You'd be right. You can just do something like this. We'd have an array of letters, and this array simply has A, D, let's say Z, let's add a few more E, R, and finally B. And if somebody asks us to sort this, well, we can just use something like a sort method that comes with most languages. And if I run this, look at that. Nice and easy, just sorted everything. I'm a genius, right? Why would companies ever ask such a simple question of us? You see, the problem is when inputs get larger and larger. Kind of like when we talked about Big O. We don't care about small inputs. That's easy to do, especially with our modern fast computers. It starts costing companies a lot of money when we have to perform operations on larger and larger data sets. That's when things become a little bit crazy and expensive. For example, Google has a ton of websites that are indexed. What if they need to sort those websites in a way? Perhaps sorting a news article based on the time that it was released. And because we're talking about Google here, we're not talking about 10 articles. We're talking about thousands, millions, and more articles sorted based on date. What about Amazon? Amazon is all about sorting. They sort their products based on category, based on price, based on rating, and they have millions of products. What about Apple? Well, Apple has the Apple Store, and they list all their apps in some form of a sorted order. Podcasts in a sorted order. What about Microsoft? Well, Microsoft, they need to sort all their logs of, let's say, their data centers around the world, so that if an incident happens, they know where it's coming from. And then Netflix? Well, they need to sort their shows, their movies, their TV shows somehow, right? And they can't usually just use a built-in sort method that comes with the language. And they usually need custom sorted methods based on the data so that they can lower their costs and lower the operations that their computers need to do. Most places sort their data or pre-process it. And all these companies, including small ones, usually sort data to make sure that it's meaningful. If it's random data that is not sorted, it's really, really hard to access. So most of the time, we sort data or pre-process it. Now, the examples that I just talked about, they are a little bit silly, but it does prove my point. For these companies, if they do something wrong or they do it in an inefficient way, it means losing a lot of money. That's why they ask these questions in an interview. They want to make sure you understand how important the topic is and that you can make the right decision as their employee. What sorting algorithm should you use based on the problem? So that's the goal of this section. I'm going to show you how to implement sorting on your own if you want. But most importantly, we're going to talk about the different sorting algorithms available to you and how you can make the right decisions for your company. And obviously, to ace that coding interview. Now, the reason that most sorting algorithm lessons get really boring is that there's so many sorting algorithms. If we search sorting algorithms on Wikipedia, you get a pretty large list. And implementing these sorts one by one yourself takes a lot of time. But most likely, you will never implement your own sorting algorithm in your life, except for maybe a simple one in an interview. Because most of these, especially the advanced ones that are really fast, are done by academics that spend years figuring out what the best, most optimal way of sorting is. And interviewers don't expect you to be able to implement every single sorting algorithm. My goal in this section is to teach you the high level, what you need to know to become a better engineer and also ace the coding interview. I'll show you how to implement some of the important sorting algorithms, but more importantly, we're going to talk about the trade-offs between them so that you're able to talk about them intelligently during an interview. For the next few videos, we're going to talk about these sorting algorithms and also a couple of bonus ones towards the end. But the key thing to remember is that as more and more data is handled by our computers, which is a big trend in computing, sorting and searching are two of the biggest computer science problems in the software world. Searching we're going to get into in the next section, but sorting is something we'll hopefully master at the end of these videos. So let's go learn how to make good decisions when it comes to sorting. Welcome back. Let's talk about sorting when it comes to specific languages. And I'm going to use JavaScript here. I'm going to be showing you different sorting algorithms that can be used with any type of data. It doesn't just have to be strings, doesn't just have to be numbers, it can be any type of data. But I also want to show you why sometimes you want to be careful when it comes to sorting. And just don't trust that your built-in method in your own language sorts data correctly. Let me demonstrate this with JavaScript. Let's say we have another array here, and this array, we'll call it basket. And this basket will have, instead of letters, we'll have some numbers. We'll have 2, 65, 34, 2, 1, and let's say 7, and one more 8. Now, we saw that when we sorted the letters, everything looked good. What happens if I sort the basket here of numbers? What do you think will happen? And I encourage you to try this with your own language as well and see what kind of results you get. Let me click run here. That's the result. Is that what you expected? That doesn't look sorted, does it? Now, this is a silly example, but it's important to demonstrate that when it comes to sorting, you want to make sure if you're not implementing it, you know how it works. For example, when it comes to JavaScript, the way it sorts numbers is that it actually converts them to string. At least that's how the sort method works. So what happens underneath the hood is instead of just comparing numbers, it does something along the lines of if it gets to 65, 65, and then it's going to grab the character code in the first index. So we can use the method char code at and give it 0. So it's going to measure the character code at 65. If I run this, I get 54. Now, 54 is Unicode. And if I go to Unicode table, this is how characters are encoded in our computers. Now, if I go to 6, I see that, we see when we hover over that it says the HTML code for it is 54. The character representation is 54. So that's what's happening here. If I do, let's say 2 here, and we'll do one more 34. And let's just console.log these so we know what's happening. And I click run. We see that 2 is 50, 65 or 6 is 54, and 34 is 51. But if I do something like 7, it's going to grab the number and it's going to be 55. So a lot of people get confused when they use a sort method like this and they don't get the response that they wanted. And that's why it's good to read the documentation of whatever you're using, such as a sort method, and understand how it works in a language. And to add even more confusion, you see here that the time and space complexity of sort cannot be guaranteed, as it is implementation dependent. Remember, JavaScript has a standard called ECMAScript. A governing body suggests what it should look like. However, how you implement it is really dependent on different engines. So the Chrome browser would use a different JavaScript implementation than, let's say, Firefox or Safari. And what kind of sort algorithm they use underneath the hood is dependent on the browser. And that's something we're actually going to talk about later on in the videos. But to finish off this section about the weirdness of sorting, let me show you one more example. Let's say I have an array of Spanish words here. Único, árbol, cosas, fútbol. And we want to sort these. What do you think will happen? Let me remove this and do this here. If I click run, I guess cosas, fútbol, árbol, único. Again, because of the Unicode characters, the A with the accent on it is not the actual A that would come before something like C, as you can see here. So in this case, to solve this problem, we would have to do something along the lines of creating a function inside of sort that takes A and B, which is the first and second item, and it's going to return A plus locale compare B, which allows us to compare these even if there were different languages. So if I run this, you see that it's now fixed and everything is working. And again, locale compare is something that you can check out and I will link to over here. Now, the reason I'm showing you this is not because we want to become JavaScript experts. Well, everybody has their own language, but to show you that there's many ways that we can sort things. And even with small little differences like this one, there's a lot of considerations that need to be had. And underneath this sort method is actually one of the algorithms that we're going to learn about in this course. And I also recommend you checking out the MDN page, which I'll link to, that shows you how you can compare different things, such as numbers, such as objects and items in an object, using the sort method. You see, in order to sort this properly, we'd have to do something like this, where we have a function inside of the sort method that will take A and B, which is the first and second item, and we'll simply say return A minus B. And if we run this, we see that our numbers are now sorted. But that's enough for now. Let's talk about the sorting algorithms that are being used in computer science in the next video. I'll see you in that one. Bye-bye. Welcome back. You see in our mind map here that we're now in the sorting section. And this big O of n log n, something we haven't talked about, is showing up. We'll get to that in this section. But I want to add a quick note here. Looking at all these sorting algorithms, and there's a lot more. It's important to note that you don't need to write a sorting algorithm from scratch, most likely ever in your career. Frameworks usually do that for us. But you do, however, need to know how they work because, well, one, you're most likely going to get asked in an interview, and two, because it makes you a better engineer. But this section is also about being efficient. You see, you can spend a lot of time on each one of these sections implementing your own and talking about it deeply. Because I don't think I've ever heard of anybody actually having to implement in code manually these sorting algorithms. Most of the time, you can just talk about it, or the interviewer tells you that the array is sorted and you need to know what to do with it. But implementing it from scratch, that doesn't really happen. But I've included it in this section because it's good to know how they work. And I'm not going to lie, coding sorting algorithms is not my favorite either. Don't let that deter you. I encourage you to watch the next couple of videos and even practice coding your own sorting algorithms because it will help your learning. But the main thing that we're going to get from this section is not how to implement these. I mean, we will do that, but the key is the trade-off. You see, we have the big O cheat sheet here that we definitely know about, right? We talked about data structures and how there's trade-offs. Well, when it comes to sorting, there's trade-offs as well. You see how there's some time complexity trade-offs, space complexity trade-offs. And it's important to know when to use what algorithm. That's our goal of this section. And before we get into our first sorting algorithm, I want to show you this nifty little tool that I'm going to link to. We have a few sorting algorithms. We have insertion sort, selection sort, bubble sort, shell, merge, heap, and then two different variations of quicksort. And we also have different data sets. This is a random data set. See how they perform when I click here based on different sorting algorithm. See that they're all working and all of them finish at different times. One is a lot slower than the other. What about nearly sorted? Again, one, such as insertion sort, is really fast while others are slower. Reversed, if the items are reversed and we need to sort a completely reversed list, again, different algorithms perform differently. It's never one that wins out over the other. Depending on the inputs, what we need to do, they're different abilities. Let's start to learn about these different types of sorting algorithms so that by the end of these videos, we can make the right decision when to use what. I'll see you in the next one. Bye-bye. Welcome back. Let's start off with the very first item on our list, bubble sort. Sounds kind of playful and nice, right? Bubble sort is part of these first three sorting algorithms here that are called elementary sorts. They're very simple, basic sorting algorithms that you would usually think of if somebody asked you to sort something at the top of your head. The second items here that we're going to get into later, merge sort and quicksort, are more complex algorithms that most of the time can be more efficient than the first ones. But to build that Lego block, let's start off with bubble sort. How does bubble sort work? Well, let me ask you a question. If I gave you a list and I asked you to sort it, in your head, imagining that you had blocks of these letters, how would you move them around? Or how would you tell a computer to move them around to sort it? And bubble sort might be one of the first things that comes into mind. You see, bubble sort comes from the idea of bubbling up the largest value using multiple pass-through. Let's see what I mean by that. We look at 6 and 5, and then say 6 is larger than 5. And then we look at 6 and 3 and say 6 is larger than 3. Let's swap them out. Then we look at 6 and 1, and once again, 6 is larger than 1. Let's swap them out. We look at 6 and 8. 8 is larger than 6, so keep it the way it is, and let's move on to the next one. 8 and 7, let's swap them out. 8 is larger than 7. 8 and 2, swap them out. 8 and 4, swap them out. We bubble up the highest number, and then we go from the beginning. 5 and 3, 5 and 1, we bubble up the largest number, so that 7 comes next. Then we keep going until 6 comes next. Then we keep looping until we bubble up the highest number one by one, until we have a sorted list. That is bubble sort. Now, before we even code this, what do you think of bubble sort? As you might have guessed, it's not the most efficient, is it? Look at how many comparisons we did, and everything was one by one, looping and looping and looping. And bubble sort is one of the simplest sorting algorithm, but also one of the least efficient. So don't hate me for showing you how this works. It's usually used as a learning tool as the first step in learning a sorting algorithm. What do you think the time complexity and space complexity of this algorithm is? The answer? Well, we can just use the big O cheat sheet. If we look at bubble sort, we see that the cases that we're most interested in is the average and worst case. We see that it's O of n squared with a space complexity of O of 1. We're not really creating any new data structures. We're just comparing items in nested loops one by one. But let's see it in code to see why this is O of n squared. And I want to challenge you here. In the next video, we're going to code along the bubble sort algorithm. But if you want, go ahead and try implementing this on your own and see how your code matches up with mine in the next video. I'll see you in that one. Bye-bye. Welcome back. Let's code our own bubble sort algorithm. I'm going to create a function called bubble sort that's going to take in an array. And I have an array up here for us of these numbers. And ideally, when we enter this array into this function, it spits out a sorted array. And based on the animation that we saw, we ideally start from the beginning, compare first and second item, swap out the items if the left one is larger than the right, and keep going until the largest item ends up in the last index, and then we loop over things again. The first thing I want to do is say that I'll just create a variable so I don't have to keep repeating myself. I'll get array.length here, which will be the length of this item, which should be 10, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Never mind, it's 11. And in here, we'll do a for loop. And we'll say let I equals to 0, which will be the first index of the array. I is less than length. I plus plus. And within here, we grab the first item. We now want to compare it to 44, and so on and so forth. We should know this by now. We want to add another for loop. J is going to equal 0. J is going to be less than length. And we'll say J plus plus. Now in here, we'll say that if array J at index of 0, so that is 99, is greater than array J plus 1, that is 44. So if 99 is greater than 44, in the first loop, we'll say, let's swap numbers. So we can simply do that by saying, creating a temporary variable that holds array at J, which the first pass, it'll be 99, and give the first index of 0 to array j plus 44, or plus 1, which is 44. And 99 now goes into the second index, so that means array j plus 1 is going to equal array j. You might need to pause the video to really understand this, but all we're doing is just swapping numbers if the left-hand side is bigger than the right-hand side. And once that is done, we increment j to 1 so that we compare index of 1 and 2, and then we compare index of 2 and 3, 3 and 4, 4 and 5, until we bubble things up, and then we go to the top and compare the items again in the outer for loop. Let's see if this works. Oh, and I just realized this array j should be temp here. So remember 99, we placed it into a temporary variable and assigning it to the index to the right. So if we run bubble sort now, we'll say numbers and we'll console log numbers to see if it's sorted. If I hit run, console log numbers, make sure I can spell. Let's hit run. And look at that. Our list is now sorted. That was bubble sort. And as you can hear, we have two nested for loops giving us O of n squared, but we're not really holding variables to another data structure or holding the numbers into other data structures. So the space complexity is O of 1. As we can see in our Big O cheat sheet, bubble sort is probably not the best algorithm, although it has good space complexity. You can use the code that I'll leave for you in this lesson to play around with. But for now, let's go on to our next sorting algorithm. Congratulations, you've just completed your first sorting algorithm, but we have more to go. So let's go to the next one. Welcome back. Let's talk about our second sorting algorithm, and it's called selection sort. Now, selection sort is, again, one of the simpler possible ways to sort a list. And the algorithm works by scanning a list of items for the smallest element, and then swapping that element for the one in the first position. Let me show you with this animation here. We start with the first item and then the second item. The red here signifies that it's the smallest item that it's seen, and the blue is scanning ahead to find the smallest item. So right now 8 is the smallest item, but we encounter 5, so 5 switches to the smallest item. We encounter 2, so 2 becomes the smallest item. We keep going, 6 is not smaller than 2, 9 isn't, 3 isn't, we encounter 1, 1 becomes the smallest item. We keep going, we find 0, so 0 becomes the smallest item, and we've just finished the list. So now we move 0 to the first index in our list. So we swap it out, and then we keep going back to the beginning, finding the smallest item through the list, which is 1, and then placing that in the second index. And we keep going like this until we find the smallest item, place it next in the list, next in the list, next in the list, until we have our list completely sorted. As you can see, with selection sort, we're still going to see a time complexity of O of n squared. If we look at the time complexity chart, we see that selection sort is not very fast, similar to bubble sort. We have those nested for loops, but uses a space complexity of O of 1. It doesn't really add any additional data besides the input. Now, using the animation that you just saw, can you implement your own selection sort? I'm going to leave this for you as an exercise. Using what you know from the bubble sort and what you just saw for selection sort, how you can use that information to sort the list using this algorithm. And I'll show you the solution in the next video. Bye-bye. Welcome back. I've left for you the solution for the selection sort. Now, I'm not going to be going one by one through each sorting algorithm because it does take a lot of time. I don't want to bore you and lose you because there's so many more exciting things happening throughout the next couple of videos. So I'll leave this for you to see how it works. It's not that much different from bubble sort. We see that with selection sort, we're setting the current index as the minimum. So the very first item in the array becomes the minimum. But when we loop through the rest of the list, we want to update the minimum if the current is lower than what we had previously. So what we had here, where we initially set the first item in the array, 99 as the minimum. As soon as we get to 44, we're going to say, oh, 44 is less than 99. Let's update the minimum so that index where 44 is now the minimum. And we're going to swap out those numbers, just like we saw in the animation. And it also is a really well-documented thing on the internet. For example, if you are a Python developer, you can just type in Python selection sort, and you'll find that, you can find how selection sorts. It's implemented in Python, and you can run the program as well. So depending on your language, you can usually click on the first or second link and show you how the algorithm is implemented. As you can see here, we have 2 nested for loops looping through the entire array, so it's O of n squared. For the rest of the sorting algorithms, I will have the code provided for you so you can play with it and interact with it. You see that the sorting works as expected, but you can also search for your own language to find the sorting algorithm so you understand it on a deeper level. Let's talk about the next sorting algorithm in the video coming up. Welcome back. I want to show you the greatest thing ever in computer science, especially when it comes to algorithms. I'm going to link to this channel because I just think is the greatest thing ever. Also, the comments are absolutely hilarious if you're nerdy like me. But somebody created a sort algorithm dance playlist where they take different sorting algorithms and show them how they work with some traditional music. Let's say traditional Romanian music, traditional Hungarian music, traditional Transylvanian Saxon folk dance. And they show different sorts. So you can check out bubble sort, which we've talked about, or selection sort, which we're doing right now, to help you with your exercise and to write your own algorithms for the exercises. Not only is the music just absolutely amazing, it really helps you with how sorting algorithms work. By the way, my favorite one is the quicksort one, which we're going to get into. It's the best dance to see, especially if you do it at 2x speed. 2x speed, these dancings become really fun to watch and really help you out. Anyway, this is a little fun thing to do with your exercises when you're trying to figure out how to write and implement your own sorting algorithms. I think this is the best way to visualize things to show you how they work. Welcome back. Up until this point, we've talked about sorting algorithms that weren't very efficient and aren't that commonly used. Now, insertion sort is not the most efficient algorithm either, but there's cases where it's actually extremely fast, which we're going to talk about. So pay attention because this one starts to get important. You see, insertion sort is useful for times when you're pretty sure the list is almost sorted or it's already sorted, which sounds silly, but sometimes this is important in computer science. And in a best case scenario, you can get O of n, or linear time, when the list is almost sorted. Let's see how it works. we have a list and we look at 6, we look at the first item and just leave it where it is. We now look at the next item, 5. And because 5 is less than 6, we switch it over. And then we go next into the list. We say, hey, 3, where are you in relation to 5 and 6? Well, it's less than those two, so we shift those over and 3 gets placed in the front. So we now have this list of 3, 5, 6. We look at 1 and say, oh yeah, that's the first item. We want to shift everything, put 1 to the left. We then look at 8. Well, 8 is larger than all those items, so let's just attach it to the end of that list. 7, well, goes between 6 and 8, so place it in there. 2, between 1 and 3, place it in there. And 4, place it between 5, or 3 and 5. And that's it. This is probably the way that your brain works if you physically had Lego blocks with these numbers and you would move things around. And this type of sorting performs really, really well when it comes to small data sets, which we'll get into later on with our exercises. But can you do this type of sorting in code? See if you can implement your own insertion sort. Same thing as before. This time, we have the insertion sort algorithm. Based on the video and the YouTube dancers that I'll link to, can you implement your own insertion algorithm? In the next video, I'll show you the answer. Welcome back. Were you able to figure out insertion sort? I have the answer here for you. Just like it happened in the animation, we first loop over the array, and if the item we're looping for is less than the first item in the array, well, we just move that item, use the unshift method in array, and add it to the first index in the array. Otherwise, if the item we're currently looping over is not less than the first index, in that case, we got to figure out where the number should go. So we're going to loop through things, do an if statement to see where the number should go, and then we move that number to the right spot using the splice method. So that if we click run here, we have our list sorted. I'll once again leave this function here for you to play around with, but I want to quickly talk about the big O complexity of insertion sort. There are times where insertion sort can work really, really well. The best case scenario for insertion sort, when the list is almost sorted or the data is really small, it can be really fast. If we go back to our little animations here, and we look at insertion sort in a nearly sorted data, and I click play, you'll notice that it's the first one that will finish. Quite fast, actually, compared to all the other ones. Let's see that again. You'll see that it's the first one done. Quite fast. And as we'll discuss in the next videos, when it comes to small data sets or data sets that are nearly sorted, you want to use insertion sort over most other sorting algorithms. Well done. Let's move on to the next sorting algorithm. Welcome back. Up until this point, we talked about sorting algorithm, bubble sort, insertion sort, selection sort, that were called elementary sorts. They were okay, but they had those nested for loops, and most of the time, it was O of n squared, which was a little bit slow. Can we do better? Well, yes we can. We're going to encounter our last big O on our list, O of n log n. Now, in order to understand what O of n log n means, we have to talk about our next sorting algorithm, merge sort and quicksort. You see, unlike bubble sort and insertion sort and selection sort, they use the technique that we've heard of before, divide and conquer. We learned about this when learning about trees. Remember, when looking through a phone book, we open up that book, not from the first page, but from the middle page. And we keep breaking up the pages until we find the name we're looking for. And merge sort and quicksort use this concept of divide and conquer and the idea of recursion, which we've talked about, to divide the problem down to do work on each subset and then combining the solutions. Now, we're going to see how this actually works, but I want to remind you that anytime we see something like divide and conquer, it usually gives you a log of n advantage. And as you can see here, it is the last piece of the puzzle, O of n log n, that actually improves, is better than O of n squared. The next couple of sorting algorithms we're going to look at are not going to have nested for loops and have O of n squared. Instead, they're going to have this time complexity, which makes things a lot better and saves companies a lot of time. In order to understand what this means, we have to start off with looking at merge sort. Let's have a look at how it works, and then I'm going to explain what the benefits are. We have the same list as before. We're going to take this list and actually divide it in half. And then we're going to divide each of these subsets into half again. And then we're going to divide those sublists into half again until we have one item. And once we have that divided up, we're going to take the first item and second item and say, hey, which one should I put first? Let's put 5 first and then 6 right after. And notice here how we're building a reverse tree in a sense. Then we look at 3 and 1 and say 1 and 3. So we're getting closer and closer to that root node. We're comparing 8 and 7. 7 comes before 8. 2 and 4. 2 before 4. And now we again combine those lists in that reverse tree, saying 5 and 1, which one comes first? 1 comes first. And then let's compare 5 and 3. 3 comes first. Then 5, then 6. Then we look on the right side. We say 7 and 2. 2 comes before 7. What about 7 and 4? 4 becomes before 7. And because we know that 7 and 8 are already sorted, we just place 7 and 8 right next to each other. And then finally, we combine these last two lists into our root node to combine the list and make it sorted. 1 and 2, 3 and 4, 5, and then 6, 7, and 8. And we have our sorted list. Now, that looked extremely complicated. A lot more complicated than the other sorting algorithms, right? Merge sort is one of the most efficient ways you can sort a list of things, and typically is going to perform better than most other sorting algorithms. And in terms of complexity, well, it's definitely a lot more complex, isn't it? We're using divide and conquer approach, which should tip you off that it's going to use some sort of recursion. The first part of n log n, that is n, comes from the fact that we're still comparing everything. We have to look at each one of the numbers and compare them in order to sort it. Now, once we divide the list into 1, which finding the middle index of these things are actually O of 1, because it's an easy mathematical operation. Get the length of the list and find the middle. But once we divide the array, we need to sort the items, which is going to take O of n. We have to look at every single item and actually sort them. And we're able to create the list. But unlike bubble sort, for example, although we have to compare everything at least once, we don't have to compare everything to everything like we did with bubble sort. All we have to do is compare their local lists to each other. Remember, with something like bubble sort or insertion sort, once we went through the list once, we then compared the next item to the rest of the list. Merge sort is also helpful because it's what we call stable, which just means that if you have equivalent elements, that is, let's say 6 and 6, or a name that is the same, it will keep the original order in the array. And this can sometimes be important depending on the type of data. Let's have a look at its big O. We see that merge sort has O of n log n, with a space complexity of O of n. Unlike bubble sort, insertion sort, and selection sort, we have a bit of a bigger space complexity because we have to hold on to that divided up list in memory. So that is one downside of merge sort. But we've now managed to make our sorting algorithm a lot faster. Now, how do we implement merge sort? I have here for you an exercise. I want to warn you, this is really difficult. Merge sort is really hard to implement and wrap your mind around. If you don't feel comfortable with recursion, it's going to be a little bit tough. Keep in mind that I'm showing you here how to do it just for your own interest. But most likely in an interview, you're never going to be asked to implement your own merge sort. You're just going to be asked maybe how it's implemented. And I've created a little skeleton to help you out here. We have the merge sort that is going to have a function that takes an array. We have the base case because we're going to use recursion here, saying that when array length is 1, remember there's only one item in the list. That is when each one of this is up at the top in its own list, we're going to just return the array. Now in here, we're going to return and we're going to merge sort the left-hand side and the right-hand side. And we're going to use this function, merge, that is going to merge the left-hand and the right-hand side. So the first step is for you to split the array down the middle in the left-hand and right-hand side in here. Then run it with the merge sort algorithm. And in the merge function, I want you to actually do the comparison. I don't expect you to get this right away. There's very few people that can do this off of the top of their head. But see if you can use all your resources available, our Discord community, or even Google, to figure out how to create your own merge sort algorithm. And I'll see you in the solution video. Bye-bye. How was merge sort? Pretty difficult, right? I have the answer for you here. And I'm not going to code along because, well, this is one of those pieces of code that me just writing in and typing it in a 30-minute video isn't really going to help your understanding. I recommend that you go through this code line by line to fully understand it. But if we take a look here, all we're doing in the first pass in the merge sort function is we're going to get the length of the array, find the middle of the array, and then we're going to slice the array into the left-hand side and the right-hand side. So that if I console log here and I click run, we see that the first time around, we're just splitting the item right down the middle, where we have 99 all the way up to 1 in the left-hand side and 5 to 0 in the right-hand side. In the next pass, because remember, we're doing recursion and this is being called again, when we get to here, we're now dividing up 99 and 44 and 6 to 1 into its own pass, and then 99 and 44 into individual items, 6 and 2, 1 into left and right, until we have everything into one item. And then we start splitting off this hand side as well. Now, what about the merge function? The merge function is going to be a little bit hard to read. But if we take a look here, all we're saying is we have a results array that we're going to fill everything with, and we're going to have a left index and a right index. And we're going to compare here. is the left index less than the length of the left array and the right index less than their right array length, which makes sure that we have items in our array? If that's the case, then let's compare our left item to the right item and push into a new array, into our results array, the item that is less. In this case, it'll be the left-hand item. And then we increment. Otherwise, if the left item is higher than the right item, we do the opposite, and the right item goes into our results. Remember, this merge function is doing what we saw in the animation. We're splitting the function down in the first part of the function, and then in the merge, we're going to take the left and right, compare it, and place it into the results array. And then go to the next, and keep doing this over and over and creating our results array. If I console log here, left and right, and I click run, we see exactly what we're doing. We have 99 and 44, and then 2 and 1. So on the left-hand side and right-hand side, 99 and 44 get compared, becomes 44 and 99. And then we compare 2 and 1, which becomes 1 and 2. Then 6 and 1 and 2, which becomes 1, 2, 6. And we keep going until the very last step, where we have two lists here. And we compare them, 0 and 1. We place 0 in the results array. And then we place 1, 2, and just keeps going and keeps going. Exactly like our animation. Now I encourage you to play around with this and perhaps go step by step. It is a really hard algorithm to get. The bad news is that the next algorithm is even more complicated. But luckily for you, as I said, you won't have to ever do this in an interview. You just need to know that merge sort is a great algorithm to use because we get O of n log n big O. Let's take a look at another sorting algorithm. Welcome back. Let's talk about our fifth sorting algorithm, quicksort. Even just from the name, you're thinking, this is going to be quick. Quicksort, just like merge sort, is a divide and conquer algorithm. Which means, and should ring a bell in your head saying that, there's probably going to be O of n log n. And if you're thinking that, you're right. You see, quicksort uses something called a pivoting technique to break the main list into smaller lists. And these smaller lists use the pivoting technique until they are sorted. But let me show you an animation of quicksort. Quicksort works like this. And if you're looking at this diagram like I am, and you're completely confused as to what is happening, this describes quicksort fairly well. It's pretty complex to understand. So let me show you a better demonstration. I have a little diagram here. Let's say we have a list that looks like this. We have 37895, 21954. What we do here is we pick a random pivot. Let's say that 4 is going to be our pivot. Once we pick this pivot item, we're going to say, all right, I want all numbers that are less than 4 to come to its left, and all numbers that are greater than 4 to come to its right. So what do? Well, we start comparing the numbers. We look at 3 and 4. All right, 3 is to the left of 4, that's fine. What about 7 and 4? 7 is higher than 4, so it should be to its right. We're going to move 4 to the left position to make space for 7. 7 jumps over to the right, and we swap the 5 that 4 came into the 7 position. And now we check 5 and 4. we got to do the same thing. We put 5 to the right of 4 and swap 9 in there. Once again, 9 is higher than 4, so 9 comes to the right of 4. Then we look at 8, same thing with 8. And then finally, 5 and 4. Well, 4 and 5 switch places. And now we have a list that has 4 as the pivot, and we know that 4 is going to be in that position in the array. And everything else to the left of it and to the right of it still needs to get sorted. But at least we know where 4 stands. From there, using divide and conquer, we now split the list. And we do the same thing. We get a pivot on the left list, which will be 2. And we say everything to the right of 2 should be higher. Everything to the left of 2 should be lower. And we have this left list sorted. On the right, we do the same thing until we split the list with 7 in the middle. And we keep breaking things down like a tree. And this is where divide and conquer comes from, until we have all the individual lists sorted and we combine them. Now, you might have 2 questions for me looking at this. One is, how do we even pick this pivot point? And that is kind of random. It really depends on the situation, but as you see here, we just happen to pick the pivot point as always the last item in the array. The second is, how am I ever going to code this? And this is pretty challenging, and I don't expect you to get it. I'll leave code for you and you can try it out if you want. But the best way to understand quicksort is my favorite Hungarian dance ever. I'm not going to play this for you. You can play it on your own, but I swear I could watch this all day. I think the dancing is awesome, the music is awesome, and, well, if you speed it up to 2 times, it's even better. Here in this video, let me mute this. You'll see that this person in the black hat is going to be the pivot, and everybody is comparing. The person in the red hat is the pointer, I guess, or the item that's being compared to the pivot. And you'll see here that as soon as we get to 2, this person is number 3, they're going to say, oop, you should be to the left of me. So they're going to dance. By the way, great dancing moves. I need to learn these steps. And 2 and 3 are now in different locations. And now we compare 0 and 3. Now, this implementation and the visual that I just showed you is a little bit different. But the idea is the same. Quicksort can be implemented in different ways, but the idea of a pivot is the same. I encourage you to watch this video to fully understand how it works underneath the hood. But let's go over the main concepts. Quicksort is really useful. And between quicksort and merge sort, I would say those are the most used sorting algorithms. You'll notice here 2 things. One is that quicksort's space complexity is really good. I mean, not as good as bubble sort or insertion sort or selection sort, but it's still better than merge sort. Its worst case is O of n squared. That is because it can be O of n squared when the pivot is the smallest or the largest item in the list, because then you're not really splitting the list in half. And because of this, you really want to make sure that you pick a good pivot for quicksort. You'll get the better space complexity, but the worst case could be bad. So in those cases, merge sort might be better. If your list was pre-sorted for whatever reason, and in that list, if we pick the pivot to be the first item or the last item, then our sorting routine here would take a very long time. Because again, the list will not really be split in half. And ideally in a quicksort, you're picking the pivot intelligently based on your list. Now, quicksort, there's a lot of variance to it and there's different implementations. But I want you to take this away from this video. Quicksort is usually the fastest on average. But the one downside is that it has some pretty nasty worst case behaviors. So if you have to guarantee no bad data, or you can't guarantee that the pivot's going to be good, then you should be avoiding quicksort. But on average, it's usually the best sorting algorithm. All right, so we've learned 5 different sorting algorithms. But the most important part is, when should I use what? In the next video, we're going to go over exactly that, followed by a fun little exercise. I'll see you in that one. Bye-bye. Welcome back. We've learned our sorting algorithms. But you might be asking yourself, Andre, I'm still kind of confused about when to use what. What about if I get asked in an interview a question about which sorting algorithm will be best if I had a user's data of 100 million names that need to be sorted? Well, let's go over some rules. 1. When should you use insertion sort? Well, insertion sort should be used with only a few items. If your input is small or items are mostly sorted, it's really, really fast. It uses very little space, and most importantly, it's really easy to implement in code. So remember this, only a few items and mostly sorted data, you should use insertion sort. What about bubble sort? To be honest, you're never going to use bubble sort. It's only really used for educational purposes as a way to teach sorting. But it's very rare that you'll find this in real life because it's just not very efficient. What about selection sort? Again, same thing with selection sort. As you can see, its numbers aren't very good, so most likely you won't be using it. Mostly it's being used as a teaching mechanism, which I did. Sorry, didn't mean to waste your time with learning selection sort, but it is important to build the foundation. What about merge sort? And this one's my favorite. Why? Well, merge sort is really, really good because of divide and conquer. We have O of n log n. It's fast, and because best, average, and worst case is always O of n log n, we always divide up the list evenly, you can always guarantee that this is going to be the case, which is not the case for most other algorithms. So if you're worried about worst case scenarios, you should use merge sort. But if you want to sort in memory on your machine and you're worried about space complexity, merge sort is going to be really expensive. It uses space complexity of O of n. However, if you had huge files that can't be sorted in memory, so you have external sorting that you need, maybe like a process outside of memory, it's suitable for external sorting, then merge sort is good because we won't care as much about space complexity then. What about quicksort? Quicksort is actually better than merge sort, right? Average case and space complexity. I mean, it has the same speed as merge sort, but less space complexity. It's probably one of the most popular sorting algorithms. But the one downside is this worst case. If you don't pick the pivot properly, you could have a really, really slow sorting. So you have to be careful. And if you're really worried about worst case, then you'd rather pick something else. Now, you might be asking yourself, Andre, what about heap sort? You haven't really talked about that. I'm going to leave resources for you so you can learn about heap sort as well. It's very similar to quicksort and merge sort, but you see here that it has a space complexity of O of 1. Isn't this better than all of the above? Well, heap sort can sort in place and doesn't have the worst case quadratic behavior that quicksort has or the memory usage that merge sort has. But on average, it's actually slower than quicksort in most cases. It's one of those things where with heap sort, unless you're really, really worried about worst case and memory, then you might use it. But most of the time, I would say you're using quicksort or merge sort. Okay, but you're saying, what about these ones down here? Bucket sort, radix sort or radix sort, and counting sort. How come you're not talking about these ones? Why can't we just use these? They look a lot better than all the other ones, especially when it comes to time complexity? Good question. Let's talk about that in the next video. Welcome back. We've talked about these 5 sorting algorithms. And by now you should know that merge sort and quicksort, although they're harder to implement, are the most often used algorithms in real life because they use divide and conquer to get us this O of n log n performance boost. But can we beat O of n log n? And here's the thing. Mathematically, it is impossible to improve on this. If anybody comes up with an algorithm that is faster than this, they're gonna be very, very rich. Mathematically, it's impossible because O of n log n means that we have to sort by comparison. All of these sorting algorithms have to compare every number to each other. But there is one exception to this rule. You can improve this if you don't make comparisons. Huh? What does that mean? There's a small section of inputs that we can actually beat O of n log n. And these are called non-comparison sorts. And you'll most likely see counting sort and radix sort. But what does that mean? Counting sort and radix sort is an entire different way to think about sorting. With comparison sort, we decided the order of the numbers based on asking the question, hey, is this element bigger than the one over there? What about the one over there and over there? And we just kept doing that. Every number got compared to each other. Non-comparison sorting does it a little bit differently. We're going to use the way that numbers and data is stored on our computers in zeros and ones and take advantage of that fact to sort things. Now, this can get pretty complex. And as you can see here in this paper, just looking at the diagrams and, for example, radix sort here and how we store numbers in zeros and ones, we can use this knowledge to actually sort some things. I'm going to leave resources for you if you want to get really technical and into this topic. I do warn you, it can get a little bit mathy. But the one thing to note here is that these type of sorting algorithm, counting sort and radix sort, only work with numbers, specifically integers, in a restricted range. So if you have only numbers that you want to sort, and the range of those numbers go from, let's say, 0 to 100, that is a small range, then you would use something like this to make things really fast. But it wouldn't work on any type of data. It only really works on numbers because of the way numbers are stored in memory. You see, unlike something like merge sort or quicksort that are universal, that is, they can sort any type of data, things like counting sort and radix sort is only useful for fixed length integers. But they are able to beat the speed of O(n) log n. And as you can see here, bucket sort, radix sort, counting sort, in their average cases, have O of n plus k, O of nk, O of nk. What n and k means is beyond the scope of this course, and some argue that in the end, this actually still turns out to be pretty slow. I'll leave resources for you, like I said, so you can read up on them, but the only thing you need to know about these is that sometimes if you have numbers that are within a certain range, it could be faster than quicksort or merge sort. So now that we know this, let's do some interview exercises based on sorting to solidify what we just learned. Welcome back. I hope your brain is not mush from all these sorting algorithms. I know I keep saying this, but sorting is one of my least favorite topics because there's just so much to learn. And most people focus on just coding sorting algorithms, which just doesn't apply in real life. Most developers and engineers go their entire life not ever coding a sorting algorithm from scratch. But we are going to encounter situations where we need to make decisions on which sorting algorithm to use. So to prepare you for that, I have a couple of questions. And the questions are numbered here, and I want you to answer each question. If this was asked to you by your employer or boss, or maybe an interview, what type of sorting algorithm you'd use based on this factor. For example, we have 10 schools around your house and you want to sort them by distance. What type of sorting algorithm will you use? And you'll see here we have about 8 questions. Give it a try. I'll link to this exercise, and in the next video, I'll give you my opinion. Remember, there's always pros and cons with everything. So really think about this, and I'll see you in the next video. Bye-bye. Welcome back. How was this exercise? Let's go step by step and see how your answers match up. First one, sort 10 schools around your house by distance. So the input is only 10. It's fairly small. We need something simple. In this case, I'll probably use insertion sort. It's really fast on small sorts. It's easy to code, and it has space complexity of O of 1. It also could be that these 10 schools are already pre-sorted or are nearly sorted on our list. So insertion is just the simplest for this type of small data. I like insertion sort for this type of things. What about this one? This one's a tough one. eBay sorts listings on their website by the current bid amount. So what would you use for this? Well, for this, I would actually use something like radix or counting sort. Because, well, a bid is usually a number between, let's say, $1 to, let's say, 50,000. Probably even less when it comes to payment on eBay. Let's say $1 to $100. These are numbers that need to be sorted, right? And because it's a fixed length of integers, integers are most likely not going to be 100 million because, well, hopefully nobody's bidding that much on eBay. So I would use radix or counting sort to beat that O of n log n time, knowing that the bids are always going to be number within a certain range. What about, not sort, sports scores on ESPN? Well, sports scores can vary. There's decimal places sometimes. There's different formats such as tennis and soccer and different things. And there's definitely lots of sports and lots of scores to handle. In this case, I'm going to use quicksort. It's going to be the most efficient. And although we might have the worst case, I doubt that the scores are going to be sorted because there's just so many different kinds. But I'm also worried about in-memory sorting. So if I used merge sort, it might be a little too much for this because of our increased space complexity versus quicksort, which, if we remember, has better space complexity. And by the way, you might have your own answer for this. Maybe you thought that the sports scores on ESPN the inputs would be a little bit different. You can have your different types of answers. The idea here in an interview situation is to explain yourself. And if you know the principles, then the interviewer is going to say, oh, he or she knows what they're talking about. Number 4, massive database. So we can't fill all this data into memory to sort it. So we probably need to sort it externally, and let's say we need to sort through past years' user data. So it's a ton of data, and we need to sort it somehow, let's say, by some sort of a date. Well, based on the information that I got here, it sounds like I need to do something called merge sort, my favorite type of sorting. And the reason I would pick this is because, well, it sounds that we're not going to be sorting really in memory because the data is so big. But because the data is so big, I'm really worried about the performance. I don't want the worst case of quicksort of O n squared. I want to make sure that no matter what, I'm going to get O of n log n. What about the 5th one? there's an almost sorted Udemy review data that needs to update and add 2 new reviews. So we have a massive list of Udemy reviews. Let's say that you rated the course and this course that you're taking has 500 reviews and you and your friend just added 2 new reviews to this course. In this case, I'm going to use insertion sort. And why is that? Well, although this data might be huge and maybe I have a lot of reviews, I'm assuming that most of the previous data is already sorted. And all I'm doing is adding 2 new reviews to this data. Insertion sort for pre-ordered lists is going to work better than any other type of sorting. Number 6, temperature records for the past 50 years in Canada. Oh boy, what should we do with this one? And this is a little tricky. I would say that first, I would use something like radix or counting sort. If the temperatures have no decimal places, if we're saying, it's minus 30 to, let's say, 40 degrees. That's a integer number between a small range. That might work well. But if I want to sort through data that also has maybe temperatures that are really accurate and have decimal places, which you can't do with radix or counting sort, then I'm probably going to use quick sort again, just so we can do some in-memory sorting and hopefully save on that space complexity. All right, last 2. Larger username database or large username database needs to be sorted. Data is very, very random. All right, so we have a username database that needs to be sorted. I'm not really sure. I don't have enough information to make a decision here. Maybe I would use merge sort if we have enough memory and memory isn't too expensive on the machine. Or maybe I'll use quick sort if I'm not too worried about worst case and that the username database isn't that large. Maybe I'll just use quick sort just to save on that memory space. And then finally, number 8, you want to teach sorting for the first time? This was a little fun question. I said bubble sort, just so I can add bubble sort to this list and selection sort. All right. Hopefully you had fun with these questions. Sorting algorithms, this is probably the funnest I can get it. Actually, no, I lied. The Hungarian dancing to sorting is the funnest you can have with sorting. But I hope you have a good idea of how to answer these questions when they come to the interview. I'll see you in the next video. Bye-bye. Welcome back. I wanted to have just a quick video to tell you about something interesting. And this depends on your language. But remember the sort method that we had in JavaScript? Or perhaps your language? I challenge you to figure out what sort of sorting algorithm it's using underneath the hood. Now, in most cases, it's either going to be quicksort or insertion sort and merge sort combined together. So go out and search what sorting algorithm your language uses. When it comes to JavaScript, there's actually no requirements to JavaScript as to which sorting algorithm to use. We have ECMAScript in JavaScript, which is the standard. But because the standard doesn't mention how this should be implemented, different browsers that have different JavaScript engines, Chrome has V8, Mozilla has its own engine, Safari its own engine, they all implement them differently. Well, last time I checked, in Mozilla, they use merge sort for sorting. And in Chrome, in the V8 engine, sort is implemented with quicksort and also insertion sort for the smaller arrays. I thought that was interesting. Anyway, I'll see you in the next video. Bye-bye. Whew, another section done. And we covered sorting, specifically sorting algorithm in this section. Most of the time, when talking about sorting algorithms, we're going to be talking about O of n log n. We learned that there's a ton of sorting algorithms, and we covered the main ones that get used more often. If you're really excited about the topic and you find this interesting, then, well, Good for you. You're one of few. I encourage you to search different sorting algorithms. But to review, quicksort you want to use when your average case performance matters more than the worst case performance. Because quicksort allows us to sort in O(n) log n, but in worst case, in O of n squared. Merge sort, on the other hand, is great because it's always O of n log n. It's also stable, which means that it always gives the same results in order if two items are the same. Although the space complexity is a little bit higher than quicksort, it's definitely a useful sort. We also talked about insertion sort, selection sort, and bubble sort. Those are fun when you're doing something quick and dirty and you want to just experiment around with sorting. But in real life, you're not going to use them. And most likely in real life, you're using the framework or languages or libraries sorting algorithm. Their advantage is that they're fairly easy to implement in code. And during the interview, you might say something like this in those rare cases that they ask you to implement a sorting algorithm. You'll say, well, because we have a time constraint, I'd like to use something naive and not efficient like bubble sort, which is slow in real life, instead of implementing something like merge sort, if it's okay with you, because we can assume that merge sort is something that we can implement with a library or fairly easily with documentation. Or you can say something like, we can just use merge sort to divide and conquer the code to make it more efficient. And this way, you show the interviewer that, yes, you can implement sorting like bubble sort, but you also know about things like merge sort to make it more efficient without having to actually implement it. So by the end of this all, I hope you now understand the trade-offs, where you can look at sorting algorithms and decide based on their speed, stability, and their readability, whether the input is already sorted or nearly sorted. How large is the input? You can make the right decision on sorting. I'll see you in the next one. Bye-bye. We've talked about recursion and sorting. We have a few more to go, and in this section, we're going to talk about searching and traversal, including breadth first search and depth first search. Searching is something we do a lot on our computers. When we talked about sorting, some of you may have been like, meh, it doesn't really sound that useful. But searching, we use that every day, don't we? We look for files on our computer. We run Command F and search for things, search for words in documents. We search Google. We search YouTube. We search hashtags on Twitter and Instagram. Searching is a big part of our lives. But how are all these computers and programs able to search things so fast? There's more and more data in this world, more and more websites to search for. How are we able to do these things so fast? How is Google able to do these things so fast? Well, in this section, we're going to build this foundation of how it all works. And we're going to be talking about a few types of searching and traversal. And hopefully, by the end of it all, you're going to understand how places like Facebook, Google, and Google Maps work when it comes to searching at a fundamental level. Let's get started. Welcome back. Let's talk about the very first type of search, linear search. In computer science, linear search or sequential search is a method of finding a target value within a list. And we should be familiar with this before because throughout the course, we've looped through arrays to find items. It sequentially checks each element of the list for the target value until a match is found, or until all the elements have been searched. Let's take a look at a visual. Linear search is simply this. We have items that can be nodes, that can be numbers, that can be anything. And we go one by one looking through the list. We check the first item, then the second item, the third, the fourth, the fifth, and the sixth. In the best case scenario, we find what we're looking for in O of one time because it's at the very beginning of the list, such as if we're looking for 6 over here. However, in worst case, we have to go through the entire list if we're looking for 9 and check every single node. Or if we're looking for something that doesn't exist, we still have to check through every single item. And this type of sorting is very familiar to us. For example, if we take a look at JavaScript, I have a list over here of beasts. And let's say we're looking for Godzilla. There's many ways that I could search for this item, Godzilla, in this list. One way of doing it in JavaScript is using index of, which gives me the index where I can find Godzilla. And this uses linear search to try and find the item. Another way is to use find index that takes a function with a condition that the item must equal Godzilla. And it's going to return true when it finds something. Again, if I run this, I get 1. Another way is to use the find function, giving it the same function as we did above, but this time it's going to return the actual item instead of the index, Godzilla. And then also finally, we also have this way of searching, the includes method that simply says, does beasts include Godzilla? And it's going to give me true or false. In this case, it's true. And your language will have different ways to implement this type of search. But all of these searches are linear searches. That is, worst case, we're going through the entire list. And as you know, our inputs or our lists can get really, really large. And linear time, O of n, is okay, but it's not the fastest. We can't use linear search to index websites like Google or search for friends like in Facebook because it's going to cost us a lot of time. Is there a better way? Well, what if the list of our data here was perhaps sorted? Would that help us in any way? Would we be able to improve? Let's say we're looking for 9 now, and we knew that the list was sorted. Let's answer that question in the next video. Welcome back. In the last video, we asked the question, is there a better way to find a number in a sorted list? And just for this example, let's add an extra number to our list. That's better. Let's say I was looking for 34, and I knew that my list, let's say array, was sorted. What's a better way to go about it instead of checking every single item one by one from left to right? Well, we can use something called binary search. Because we know the list is sorted, we can discard half the items instead of one at a time. Let me show you. We can start in the middle of the list and say, is 9 higher or lower than 34? Well, 34 is higher than 9, so let's discard everything to the left of it. And then we go to the middle index again. In this case, there's no technically a medium, so let's just choose 12 to go to the left of the medium. Is 12 higher or lower than 34? Well, it's definitely lower, so let's remove everything to the left of it. And then let's find the middle index. And, oh, we just found 34. Instead of going through the item one by one, we did that in 3 operations. And this looks familiar, right? And it's something we learned about when we talked about trees, specifically binary search trees. Because if our data is sorted, we can do better than O of n, or linear time. Because this sorted list might remind you of something. We're essentially creating a binary search tree. Unlike linear search, we can discard half the items instead of one at a time. And you might be thinking, well, that's ridiculous, Andre, because in order for us to even search this, we had to sort the list first, and that takes computational power, right? But storing data in a data structure like a tree instead of a linear data structure like an array is actually more efficient. And this is something we've already discussed with tree data structures. As we insert items, if we sort them, it actually gives us better performance than adding it to an unsorted list that we have to search through one day. And because in a tree where we make a decision, should we go left or right? Should we go left or right? And we discard half the items every step. This should trigger something in your brain that's saying, oh, this is a divide and conquer approach, which gives us a log of n time. Because log of n comes from the fact that we're not visiting all nodes. Each step down the tree, we're eliminating nodes. So this is the deal with binary search. You split a list of a sorted item and decide from there whether item you're looking for is in the left or the right of the list. And because the list is sorted, you can make that decision very easily by just comparing things. And we just keep going until we find what we want. In this case, number 34. We make 1, 2, 3 decisions. And this makes sense because if you're a teacher that's looking at a stack of essays and papers by students, if that stack of paper is not organized, then you have to go through it one by one to find, let's say, Timmy. But if the stack of paper is sorted alphabetically, then you can find Timmy by dividing the papers half each time until you get to Timmy, just like a phone book. We start with n elements. Then when we step down, we have n divided by 2 elements remaining. And as we step down, we have n divided by 4 elements remaining. And we keep going until we find our element. And in the sorting section, we learned that merge sort and quicksort are doing the same thing. And we also learned how to actually search through this tree in our data structure section, right? With linear search, we had for loops. With a binary search tree like this one, well, we had our lookup method, where we checked the left node and the right node and divided up the list using a while loop in half each time. So we know how to do linear search and binary search. We know that binary search is going to be log of n, time complexity, versus linear search, which is O of n. But what are these two? Well, up until this point, we've talked about when we're searching for an item, where we know that 34 exists, our list is sorted in a binary search tree, and we know where to go, left or right. But sometimes we have to do something called traversals. And traversal simply means, well, going from node to node, either finding a specific thing or making sure that you touch every single node. Perhaps we want to add a color attribute to each node here. Perhaps we want to update these numbers and multiply them by 2. In that case, we have to visit every single node. How do we do that? Let's find out in the next video. There are times when we want to do something called traversal. And the name traversal and search is often used interchangeably, sometimes meaning the same thing, sometimes not. Up until now, we talked about binary search trees. And we knew what we were looking for, and we always knew where to go, left or right. But other times, we want to do some operations on the same node. As I mentioned before, we might want to add a color property to this node. Perhaps if we had a user node, we want to add an age property to all our users that are in a tree structure. Perhaps we want to add a shape property to these nodes. Or perhaps we don't have a sorted tree. It's not a binary search tree. Or we have a graph that has no order to it, in which case we have to visit every node. Or maybe we're working at Google and our boss asked us to, hey, can you check if our binary search tree we entered into our database is correct and that it's actually valid, and making sure that the left item is always lower than the right item. And in order for us to check that, we have to touch every single node. But how would we go about doing this? You can think of traversals as visiting every node. And as you can imagine, because we're visiting every node, that's an O of n operation, linear time. Up until now, we did loops to visit all of our other data structures, like arrays, linked lists, hash tables, queues, stacks. So how do we go about doing this in a data structure like a tree or even a graph? Well, luckily for us, there's two ways of doing this that we need to learn. One, it's right over here. Do we have to do a tree traversal or do we have to do a graph traversal? In that case, our two options are the exact same. We have breadth first search and depth first search. And sometimes this is called traversal instead of search. As you can see, both with trees and graphs, it's the same thing. The big O is O of n because we have to visit every single node using these two techniques. But let's review why this is important and why we don't store everything in just lists, which are simpler to understand. Well, the main benefit of why we don't put complex data into just lists, like arrays that are sorted, is that we get the O of log n searching. What about hash tables? Those are easy. Well, remember that hash tables aren't ordered. And at the end of the day, we represent data with different data structures based on their needs. And trees and graphs work really well for a lot of cases, which we've already discussed. When we search for things, we have the benefit, but also when we insert or delete items, we have better performance than something like an array. But we also maintain the order that we wouldn't have otherwise with hash tables. Trees and graphs are used a lot when we want to search nodes or visit every node, and it represents a lot of data that models the real world. Now, let's explore how these two traversal techniques work. I'll see you in the next one. Bye-bye. Welcome back. Let's look at the first of the two types of searching or traversing a tree or a graph. It's called breadth first search. Try saying that 5 times really fast. The way breadth first search works is that you start with the root node and move left to right across the second level, then move left to right across the third level, and so on and so forth. You just keep going from left to right, level by level. And you keep going until you find the node you're looking for, or the tree ends. Let's have a look at another visual. Breadth first search works like this. We go to the root node, then the second level, the third level, and then finally the fourth level. And you can see here how they're numbered, going one by one, one by one. Now we're going to code breadth first search and understand how it works, but I want to mention that breadth first search uses additional memory because it is necessary to track the child nodes of all the nodes on a given level while searching that level. This means that we need to track every node and its children in order. And we're going to talk about some of those implications when we code breadth first search and also look at the pros and cons compared to the other kind, depth first search. But let's go to our code for a quick example. We have here the tree that we created in our tree data structure section, a binary search tree that creates a tree for us that looks like this. 9 is the root node. We have 4 and 20, 1, 6, 15, and 170. If we did breadth first search, what would you think the order would be if we wanted to convert that into a list? Well, we'd first visit 9, then we'd visit the second level, 4, then 20, And then we visit the third level. Again, going from left to right, we'd visit 1, then 6, then 15, then 170. And using breadth first search, we're able to create this list. Let's have a look at the second way of traversing a tree or a graph, and that is depth first search. Let's have a look. Depth first search, unlike a breadth first search, is a little bit different. The search follows one branch of the tree down as many levels as possible until the target node is found or the end is reached. When the search can't go on any further, it continues at the nearest ancestor with an unexplored child. Let me show you. We start off with 9, then we go to 6, then we go to 1, and we've reached a leaf node. There's no more children. So we go back up to 6 to our ancestor and then see if there's any more unexplored children. In this case, we haven't gone to 4, so let's go back up to 4. And now we go up because there's no more children all the way up to 9 and say, all right, let's go to the right now. We go to 12, then 34, and then come back up and then search 45 as well. Now, depth first search has a lower memory requirement than breadth first search because it's not necessary to store all the child pointers at each level, something that we'll see when we actually code it. The idea with depth first search is that we want to go as deep as possible into a graph, usually starting from the left side, and then start going to the right until the traversal of the tree is done. As the name suggests, we go depth first, that is deep first, versus breadth. Depth first search looks something like this. Once again, we go all the way down, come back up, all the way down, come back up, all the way down, come back up, all the way down. As you can see, going deep first, then keep going to the right. And I like to think of depth first search as like walking through a maze, right? We're going as far as we can, and when we hit a dead end, well, you turn back around and go to the next point where you can make perhaps a left or a right turn until you get to the end of the maze or the maze ends. So if we go back to our code and we look at breadth first search, we did here breadth first search. What about depth first search? How would that look? Well, from what we know, and hint, hint, there's going to be different variations of depth first search coming up. But from what we know, we would start off with 9, then 4, then 1, then go back up to 4, and then find 6, go back up, find 20, go to the left 15, and go to the right 170. So our list is a little bit different than breadth first search. We have different orders. But why do we have these two ways of exploring a tree or a graph? What's the pros and cons? And up until now, I've just been talking, but you might not understand why one is better than the other. And before we implement this into code, I want to go over the pros and cons of each. So let's do that in the next video. I like to think of breadth first search as a water flooding from the top, kind of like this, where we check from the top all the way down. And I like to think of breadth first search as these little lines that go one as deep as they can, and then they keep going to the right. But what is the advantage over the other? They both do the same thing, traversal, but each one is used for different reasons. And in interviews, you'll get questions about what type of traversal to do. And usually you'll have one of these two answers that you'll have to say. So when should you use one over the other? And we're going to explore that throughout the next couple of videos. But I want to start off with the main pros and cons. The time complexity for breadth first search and depth first search is the same, right? They all visit the nodes at least once. So it's O of n. All traversal is O of n. So when we're trying to traverse through a tree or a graph, we're really trying to do is walk through the tree without ever repeating ourselves. And the order is the thing that matters when it comes to breadth first search and depth first search. Now, let's talk about breadth first search. With breadth first search, it's very good for finding the shortest path between a starting point and any other reachable node. Because we always start off with the root node and then search the closest nodes first. And then the nodes further, and then further, and then further. And this is going to become more apparent when we talk about graph traversal. And we have some videos specifically for this discussion. But the one downside with breadth first search is that it requires more memory than depth first search. Again, something we'll discuss more of when we start coding it. But a good rule of thumb is that if you have additional information on the location of the target node, and you know that the node is likely in the upper level of a tree, then breadth first search is better because it will search through the closest nodes first. On the other hand, depth first search is the opposite. If you know that the node is likely at the lower level of a tree, perhaps depth first search is better in that case. And depth first search is really good at asking the question, does the path exist to a certain node, from a source node to a target node? Again, something we'll get more into when we talk about graphs. The big advantage with depth first search is that it uses less memory than breadth first search. The downside with depth first search is that it can get slow, especially if the tree or graph is really, really deep. And it's not necessarily good at finding the shortest path, like breadth first search. Now that we have an idea of when to use what, I know it's not 100% yet, we're getting there. But first I want to do a bit of an exercise. Welcome back. Let's do a little exercise with just the general information we have about these two traversal techniques. I have questions here for you, and underneath it, I want you to answer whether you should use breadth first search or depth first search. And these are the type of questions that you're going to get asked in an interview, and it's good to understand. I know that our knowledge isn't complete yet because we haven't coded anything, but I want to lay the foundation so that when we start coding, you understand why we have these things. So give it a go. Try and answer these questions, and in the next video, I'll go over the solutions. Bye-bye. Welcome back. How was this exercise? Hopefully it wasn't too difficult. If you're able to answer these questions, you're most likely going to be okay in an interview if you ever get asked about depth first search or breadth first search. So let's go over the answers. If you know a solution is not far from the root of the tree, well, we talked about this. We want to use breadth first search because it starts searching the closest nodes to the parent first. If the tree is very deep and solutions are rare, well, this is a bit of a tougher question, but we would use breadth first search. And the reason we would do that over something like depth first search is that depth first search will take a really long time with this type of a tree. Because the tree is really deep, it's going to go one by one, going really, really down below. And because solutions are rare, it's most likely going to just repeat that step over and over and over. And as you'll see with depth first search, we use recursive functions. And with depth first search, that can take a really, really long time. Although with this one, we also have some memory concerns with breadth first search. So your answers may vary, but this is what I would use. As long as you can explain that to the interviewer, you're fine though. What if the tree is very wide? That is, there's a lot of nodes. It's not a binary tree, it just has a ton of nodes underneath each parent. Again, this is a bit of a tougher one, but we want to use depth first search. Because a breadth first search, and I'm going to say BFS from now, is, well, it's going to need too much too much memory. The way breadth first search works is that it has to keep track of the nodes in the current level in something called a queue that we will see. So because of that, it might take up too much memory. What about the next one? If the solutions are frequent but located deep in the tree? Well, in that case, we'd use depth first search. So hopefully we'll be able to find an answer quicker than breadth first search. What about the next one? Determining whether a path exists between two nodes. That is what depth first search is built for. What about finding the shortest path? That is for breadth first search. Now, keep this document in mind and revisit it as we learn more and more about these two algorithms, because things are going to start making sense more and more. But this is a good sheet to keep in mind before you go to an interview in case you get asked these questions. Enough talking for now. I think it's time for us to start coding these algorithms. I'll see you in the next one. Bye-bye. Welcome back. Let's start to code our very first algorithm with breadth first search. If you remember, with breadth first search, we have to go from the top, then to the left, and then visit all the nodes in that level. And when I said that it uses a lot of memory, is that when it visits 6 and 12, from there, it's going to go back to 1, 4, then 34, then 45. So as it goes through this level, we need to keep a reference to all the children nodes of every node that we visit so that we can go back to them and visit 1 and 4. That's where the memory is coming from, because we have to keep track of those children of the level that we're on. And you'll also notice this path that we're taking from 9 to 6 to 12 to 1 to 4 to 34, 45. We're going to be using a queue data structure, which allows us to keep a reference to the nodes that we want to come back to. Because we know 6 is in front of 12, we can go back to it and discover its child nodes. So let's get coding with our breadth first search algorithm. We have over here our binary search tree from our tree data structure section. We've already implemented the insert, lookup, remove methods, and we've created this binary search tree that gives us this type of tree. Let's remove these for now and start coding our own breadth first search implementation. And ideally, by calling this function, we get a list of all these items in the order of breadth first search. That is 9, 4, 20, 1, 6, 15, 1, 17. Let's call this breadth first search. And within here, we need 3 things. One is the current node, which will start with the root node. And we need 2 other things. One is the actual list that will be our answer. We'll have an array here where we insert these numbers into in the order of breadth first search. And we also need a queue data structure, which we'll use an array for this example, to keep track of the level we're at so that we can access the children once we go through it. Remember, we're going to keep track of 9, then we're going to keep track of 6 and 12. And when we get to 6 and 12, that's going to be in our queue, but we have to go back once we're at the end of that level to 6 so that we can discover 1 and 4. So that's what the queue will be used for. Now, the very first thing we're going to do is to add to the queue the very first item, the root node. So we're going to say queue.push current node. Now, what we need to do here is go from the current node down to our children node. And again, go from left to right, and then go to their children node and go from left to right. And the way we're going to do that is to use a while loop. And we'll say that as long as queue.length is going to be greater than 0, that is, we have nothing left in the queue, in that case, we'll say that the current node will be queue.shift. And shift simply means that we take the very first item in the queue. Remember, a queue is just a lineup to the roller coaster, and the first person that comes in gets to go first on the roller coaster. And shift simply returns and removes the first item in the queue. In our case, we'll have 9 as the first item in the queue, the 9 node, and we're going to shift that and assign it to the current node. And because this is the root node, we want to start off in our answer that the list will have the number 9 at the top. Let's move this up here just so you can see better. So the first thing we're going to do is say list.push the current node.value, which will be 9. So we have the first answer in our list, which is 9. From there, we're going to say, hey, does the 9 node have a left child? Because if it does, let's add it to the queue, saying that we need to check out that node, and we'll push it to the queue, current node.left. So what we just did here is we've added 4 to the queue. And then we also want to add 20 to the queue. So I'm going to say if, after you've added 4 to the queue, I'm going to say, hey, does the current node have a right node, child node? In that case, we'll add it to the queue again as the second item in the queue, and the current node.right will be pushed to the queue. And this is the amazing thing of what we just did. Now that the queue has 2 items, as it passes through, it'll have 4 and 20. It's going to loop through, come to this line, and say queue.shift is going to grab 4 and say push 4 to the list. And then it's going to say, hey, does 4 have a left child? Yes, it does. It has 1. Well, then add it to the queue. So 1 gets added to the queue that has 4, 20, and now 1. And then we say, hey, does 4 have a right child? Yes, we have 6. Well, we're going to add that to the queue again. So we're going to have 4, 20, 1, 6. And then we go back to the top and say, what's next in line? Well, we have 20. So let's shift 20, grab that, remove that from our queue, and go through it again. Again, left child would be 15, and right child would be 170. If we console.log here, our current node.value, and actually, let's just log it down here, which will be the shifted node. That is the node that we're going to be operating on and checking. Oh, and we'll have to actually call that. So let's do tree.breadth first search. And I click run. We see that I'm checking 9, then I'm checking 4, then I'm checking 20, then I'm checking 1, then 6, then 15, then 170. Very, very cool. And we're pushing that to the list every time. So all we need to do at the end is just say return list. So that if I run this, look at that. I have my breadth first search that returns 9, then 4, then 20, then 1, 6, 15, and 170. That wasn't too bad, was it? We see from this code here that it's quite simple. And the only issue that we have is that this queue can get pretty large because we have to keep reference to our child nodes. The memory consumption that can really hurt us is this queue that we keep adding to. we keep popping things, but we also add to the queue. So that if we have a really wide tree, instead of a binary tree where we just have a left and a right, and maybe we have 10 child nodes, this queue can get pretty big. And depending on the data, that memory consumption might be big. And that's one of the main downside with breadth first search. But hopefully you see the simplicity of breadth first search. Wasn't too bad, was it? All right, I'll see you in the next video. Bye-bye. All right, we're going to do this just for fun. Usually breadth first search is implemented the way we saw it, just using a iterative approach. But for fun, I want to see if we can do a recursive breadth first search. And in order for us to do a recursive breadth first search, we can create a new function. We'll have R here for recursive. And in here, we need to create a base case, when to stop. And we will stop if q dot length is 0. Or we can just say when q dot length is 0, like this. If that's the case, we want to have our base case and return the list. But you'll notice here that I haven't defined what queue and list is, like I did with our iterative approach. And that's because if I go to the top here and declare these variables like I did, because in a recursive function, this function will be called over and over, we're going to be resetting these variables and lists over and over to an empty array. So the way we would do this in a recursive function is that we need to actually pass queue and list as a parameter. So that when we call it down here, instead of doing it this way, we'd have to say that the queue will have the this.root node. But remember, the queue has to be an array, so we just wrap this in curly brackets. And in JavaScript, this shows that we have an array with item of this.root, kind of like we did with breadth first search the first time around, right? The initial queue had the current node, which was this.root, our root node. And then the second parameter would be the list, our answer, which will start off with an empty array. So now that we have these, and that's a bit of a gotcha when it comes to recursive functions, we can now do something similar to what we did the first time around with our iterative approach. We'll say that our current node, let's use let here, let current node equal to this dot queue dot shift. Again, same thing as we did up above over here. To grab the current node. And then we can actually just copy what we did over here. If current node left, queue push the left node. If current node has a right child, then push it to the queue as well. So I'm just going to copy this and add it over here. Make sure the indentation is working. That's better. And finally, because this is a recursive function, we want to return the function so that it goes through again, and this time giving it the queue and the list. And I know this can get a little bit confusing. You might have to look at it. But going through it step by step in your head, you might want to grab this code after this video to see how it works. It's not that much different from the iterative approach. And because this is referring to a method inside of a class, the way it works in JavaScript is we have to say this dot breadth first search, which refers to the class, use the method within this class. And I notice here that we don't need this for the queue because queue is just a parameter. Now, we also want to make sure that we push to the list when we're in here. So just like we did above, we're going to say list.push the current node.value. Again, exactly like we've done above here, we want to push the list, the value to the list, because the list is our answer. Now, if I click run here, I'm going to get an error. And this is a bit of a gotcha, a little bit JavaScript specific. And one of the reasons that can get frustrating with JavaScript is that this keyword only works when we're inside of the class, the binary search tree class. Outside of this, remember that we have the tree class that we instantiated. So this is tree.root. And if we run this, we now have our list, this time done recursively. I'll leave this for you to play around with and see which one you like better. But both of these now give us the same results. 9, 4, 9, 4, 20, 1, 6, 15, 170. I'll see you in the next video. Bye-bye. Welcome back. Let's talk about depth first search now. We've implemented our breadth first search and we feel comfortable for that. But what about depth first search? Going down our tree and exploring the deepest part of that tree before we come back up and explore the right side of the tree as well. And when it comes to depth first search, we have to be aware that there's 3 ways that we can actually implement it. It's called in order, pre-order, and post-order. Remember how we had the list that we got with breadth first search? Well, there's 3 different orders that we can return this list with depth first search. The first one is called in order. And it looks something like this. We go with 33, 101, 105. It's called in order because in a binary search tree, it gives everything in order. If we take a look at this list or this tree, ideally in a in order traversal using depth first search, we would get something like this. We would get 1, then 4, then 6, because we go 1, 4, 6, and then we go 9, and then we go all the way down to 15, and then we come back up to 20, and then to 170. It's in order because, well, look at that. Everything is in order. So this is really useful if you have a binary search tree like this. Another way that you could return it is called pre-order. And pre-order starts off from the parent node down to 33 and then down to 105. So we start off with the parent and then grab the child nodes left to right. In our case, it would look something like this. We would start off with 9 because it's the parent one. And then we grab 4 because it's the next one in the list. And then we go 1 as we're traversing all the way down. Remember, we're doing depth first search, so all the way down. And because we got to the very bottom, we now go back up and down to 6. So we see here we did 4, 1, 6. And then we go to the right side to 20. And then grab 15, then 170. And you're asking yourself, this seems kind of useless. Why would we ever want to use pre-order? I mean, in order, we had everything in order. Why would we ever need this? And pre-order is really useful if you want to, for example, recreate a tree, right? Because with pre-order, I can just go 9 is the root node. Then we have 4 as the left-hand side, 1 as the left-hand side. And then from there, we have 6 on the right, 20 to the right of 9, 15, and then 170. We can recreate a tree really easily because it's ordered for us versus the in order method that didn't have that order that we wanted if we wanted to recreate a tree. Another way, And the last way to do this is called post order. And post order is the last option. That is going all the way down, grabbing 33 and 105, then going to the top, to the parent. So 33, 105, 101. So in our case, a post-ordered depth first search will look like 1, then 6, then 4, and then going back up all the way down to 15, then 170, then 20, and then finally 9. We search the left-hand side first, the children come before the parent, and then we search the right-hand side first, and the children come before the parent. Now, these 3 types of ordering are really specific, and although it may look confusing right now, you'll see that when we write it in code, it's not that difficult. You just need to know that when it comes to depth first search, you have these 3 types of traversals that you can do that you may want to implement depending on your needs. But the easiest way to show you how this works is, well, to actually do it and code it. So let's do that in the next video. Welcome back. Let's implement depth first search using in order, pre-order, and post order. And we're going to start off with in order first. Now, let's name this, let's call it depth first traversal, or search in this case, and we'll say in order. Now, within here, we're going to use a recursion because, well, most of the time depth first search is implemented using recursion because it's quite simple to do so, as you'll see. But if you remember from implementing breadth first search, with recursion, because we're going to be calling this function over and over, we can't just declare variables inside of it because they'll be reset. So we're going to do the same thing as we did here. But to keep things clean and to also show you how different ordered depth first searches work, because we're going to have 3 of them. We're going to have in order, post order, and pre-order. I'm going to create 3 separate functions down here describing these. So all I'm going to say in here is we're going to have return traverse in order function. This will be our recursive function. And DFS in order method simply returns whatever gives us this result. So in our case, we're going to add this.root, start off with our root node, and we're going to give it a list where our answers will be entered. And we're going to do the same thing for post order and pre-order, just naming them their appropriate ways. So let's write the first function. Traverse, if I can spell, traverse, post order, and pre-order. There you go. Let's start off with the first one. It's going to be a function called traverse in order that we created up above. That's going to get a node and some sort of data, or we can call it list in this case. Now remember that in order is going to give us the list of nodes in order, in sorted order. If we look at our tree, we want to ideally have 1, 4, 6, 9, 15, 20, 170. And the way we go about doing that is, well, first of all, we're going to check, hey, does the node have a left child? If it does, well then, we're going to traverse all the way down using recursion to node.left and pass data. Again, I know recursion can be tough to grasp at first, but all we're saying here is that if the node, especially the root node when we first start off, if it has a left child, which 9 does, then traverse all the way down. keep going left. It's going to call this function, and it's going to keep going left until the node has no more children, and we end up at 1. When we end up at 1, I want you to, well, list.push our answer, node.value. So once there's no more node left, that is, we're at 1, then go to the next step, which is to push this value 1 to the list. After that, we're going to do the same thing we did up here to the right. That is, we want to go to check the right now and say, hey, go all the way to the right until there's no more children. And now we have 6. And we go through this function once again. When we have 6, there's no left child, and it's going to push the current node value, which is 6, to the right. So let's actually console log this. And by the way, we want to return, remember, we want to return the list at the end. So I'm going to console.log node.value. And if I click run here, or let's make sure this works, so I'm going to say traverse in order. I'm going to comment out these two and say tree.dfs in order, and we're just going to run this. If I run this, I get data is not defined because, well, this has to be list over here. Past the list. There you go. Let's run. And look at that. We have 1, 4, 6, 9, 15, 20, 170. And we see here the path that we took because I console logged here, right? We have 9, 4, 1, then 6. Then we go back to 20, 15, then 170. But because we're pushing our answers to the list, after we've verified the left nodes and traversed all the way down, the lowest numbers get put into the list. Now, the beauty of this is that implementing the other two now becomes extremely easy because they're very similar. Just the order changes. So the next one, which is traverse, let's say, pre-order, the only difference now is that, well, we got to make sure that we recursively call the right name. The only difference is that with pre-order, we want to push at the very beginning before we get to the very left node. Because remember, in a pre-order traversal, we go 9, 4, 1, 6, then 20, 15, 170. We start with the parent first, and that's the order. So we push the parent first, which is 9, then we grab 4, then 1, then we get 6, then 20, then 15, then 170. Let's see if that works. I'm going to change this to pre-order. Make sure I spell that right. Pre-order, perfect. And then I hit run. And look at that. We went 9, 4, 1, 6, 20, 15, 170. In that order, in the list. Now here, you can pause the video and see if you can implement the last one yourself. It should be fairly simple, right? All right, I'm going to get going. The post order is going to be very similar. We'll say traverse. Post order will have the list push at the very end. And why is that? Because we check 1, 6, the left and the right, and then the top, 4, then 15, 170, 20, then 9. So the order, as the name suggests, is post, is at the end. So if I change this to post order now, and I hit run, we have, well, the wrong order because I need to make sure I change the names So it's recursive. So we say traverse post order, not pre-order. And if I hit run, that's much better. We go 9, 4, 1, and we start adding this to the list. I go 1, 6, 4, then 15, 170, 20, and then 9. And if we print all of these out, and I click run, well, let's remove the console logs from here and just console log each one of these. If I hit run, there's our logs. We have the post order, we have the pre-order, and then we have the in order. All of them are depth first searches, just done in different orders. Now, I'll leave the code for you to explore here. Because it is recursion, it might take a bit of time to get your mind wrapped around it, but you see here that it wasn't that difficult. We implemented breadth first search, both iteratively and recursively, and we also used depth first search in order, post order, and pre-order. And if you think about it, it starts to become more and more clear, especially when it comes to depth first search. All we're doing is we're checking the left element and the right element, or the right node. So that is the left reference and right reference of each node. And sure, we're doing these actions in different order sometimes, depending on which ordering strategy we choose. But we're still doing the same three things. We're checking the left, checking the right, or we're just pushing a node to our list, to our answer. And for those of you that may have realized, we're using a stack data structure right here with the recursion. Each of these functions are added to our call stack and will start to return as they reach the end. That is, there's no more left and right children. And this is important to understand because it shows the space complexity of depth first search. The amount of space that we need in terms of memory, unlike breadth first search, which used the queue, the height of the tree will tell us how much memory we'll need because the height of the tree will match the deepest recursive function. And that's what's going to be added to the stack as memory. So our memory consumption is O of height of the tree, which will give us the worst case scenario when using depth first search. So now that you understand better how these searches or traversal work, I encourage you to go step by step, code your own, see if you can add this to your tree data structure as well. Because the beauty is, once you know how this works, you also just learn how to traverse through a graph. Congratulations, and I'll see you in the next video. Welcome back. The beauty of what we just learned in tree traversal, which was O of n, we're visiting every node, is that it's the same as in graph traversal, because trees are just simply a type of graph. So using the same technique, instead of using left and right properties, perhaps there's 10 children, well, we can do the same thing using depth first search and breadth first search. And this is really powerful, right? Because graphs are used to model real life models, such as a recommendation engine in Amazon. We can now see what type of items are perhaps related or the closest relation to the last book that we bought. And in that case, they would use something like breadth first search. Or on Facebook to see what type of friend requests I should be recommended. If I have a connection on LinkedIn, perhaps, I might use depth first search to see what degree of connection I have with that really important CEO. We use depth first search. And these are the bases of how peer-to-peer networks work, how Google Maps works, right? which is really, really powerful. And I have a nice visual here. I have our visual algo here, our good friend, and they have depth first search. And I made this little graph, and we can traverse now using, actually let's do breadth first search first. And we'll start off with 0. So I'm going to enter 0 in here and see how depth first search would work. We check all the closest nodes, 1, 3, 4, 5, 6, and then we start with 1. Does it have any children? Yep. 2, 7, and 8. And then we go next in line. 3, what about 4? What about 5? What about 6? They don't have any children? Okay, let's go keep going down to the next place that has children. And we traverse the graph, as you can see, starting with our closest neighbors and then going further and further out. With a depth first search, let's say we're starting at 0, and I hit go. We go to 1, then 2, then 7, and then we're going to keep going deeper. 8, we're going to go to 9, then 10. There's no more nodes, so we're going to go all the way back and go to the next in the list. That is 3, then 4, then 5, then 6. So just by looking at this, you might see what I meant when I gave you the information at the beginning of this section. That is, breadth first search is usually good for shortest path. That is, what's the closest to our node? What are the most related items on Amazon? Who are our closest friends on Facebook or closest connections on LinkedIn? Versus depth first search, which is really good to see if something exists. With depth first search, we're able to go really deep into a graph fairly fast than breadth first search that might cost a bit of extra memory. Let's talk about these two algorithms in more detail when it comes to graphs. Welcome back. I encourage you to play with Visual Algo and create your own graph as I talk throughout these videos about depth first search and breadth first search when it comes to graph traversal. The way you can create a graph is to just simply say draw graph, and you'll be able to create something like this yourself. And then you can explore both depth first and breadth first searches. Now, I'm going to have this animation running while I'm talking, but we'll start off with 0 and do a breadth first search. The unique thing about breadth first search is that it lends itself really nicely to determining the shortest path between any node. Especially when it comes to saying, hey, what's the closest node to 0? That's a really easy question to ask when it comes to breadth first search. And we've already talked about how that is used in recommendation engines, peer-to-peer networks, even Google Maps, right? Facebook friend requests, and Instagram recommendations. Breadth first search, or BFS, allows us to convert a graph essentially into a tree, because we know who the children of the parent node is, and then the grandchildren, and then so on and so forth. So if we remember this diagram over here, we now understand that breadth first search, yes, it uses more memory to keep track of the parent nodes and the children nodes of that level. But it also helps us determine the shortest path, and it's better if we know that a node we're looking for is close to us, because it's going to look at the closer nodes first. So that when you get asked this in an interview, you know this algorithm is going to work well for these types of questions. Because breadth first search is crafted to help us determine the shortest path between two nodes in a graph. What about depth first search in graphs? You might not know it, but you just learned how to solve a maze using programming. Because depth first search is exactly like solving a maze, right? If you've ever done a real-life maze yourself or looked at a program that tries to solve which path to take, The idea was to go as deep as you can, and when you hit a roadblock or a place where you can't go anymore, you backtrack and find a different route. And then you keep backtracking until you find the desired node or you exit the maze. And that's the beauty of depth first search. You can now implement an algorithm that solves a maze puzzle. Isn't that cool? Just like in here, if we do a depth first search, let's say we're starting at number 1 and 10 is the exit or 9 is the exit. And actually 1 won't work because this, unlike our previous graph, which was undirected, that is, it had both directions, I can go back and forth. This one is a directed graph that has specific directions that it can go. So let's do 0 to 9. If I do depth first search and do 9, or we'll start at 0, trying to find 9. Just like looking through a maze, I go here, I keep going through my children, and then try and go as deep as I can. And I manage to get out of the maze before I even search 6 and 5 over here. And obviously this algorithm keeps going because I didn't tell it to stop at 9. But you see how it was exactly like solving a maze. And that's why we use recursion for depth first search, right? The idea of backtracking after a dead end and then repeating the walk down another path is just recursion. Each step smaller than the other, and then we go back and then keep doing the same thing over and over. The idea of depth first search is that it's really good at saying, does the path exist? It doesn't tell us the shortest path, but whether it even exists. And it uses less memory than depth first search. The one downside with it is that if you have a really, really deep graph, then it can get very slow because the deeper the graph, the more recursive calls, the more space complexity you add because we have to keep track of those function calls on a stack. Welcome back. I wanted to talk about one last piece of the puzzle, especially when it comes to graphs. Although we've talked about graph traversal up until now, and also tree traversal that use BFS and DFS, there's also another thing that you should consider. Now, in an interview, you're most likely not going to implement these algorithms because they're extremely complicated and they take a long time. However, an interviewer might expect you to know about them and know that you'd use Bellman-Ford or Dijkstra's algorithm to figure out a shortest path problem. But you might be asking yourself, whoa, Andre, you just told me that breadth first search is used for the shortest path problems. Why do we need these extra algorithms? I already know how to do that. And this is actually a special case. You see, breadth first search is great for the shortest path problem, but there's one thing that it can't do. It assumes that each jump to another node in a graph, if we go back here, it assumes that each path has the same weight. With a depth first search and a breadth first search, we don't really care what kind of weight an edge has. For example, in real life, such as Google Maps, some roads are faster than the others, right? We have perhaps more traffic on one road. Maybe the distance from one node to another is shorter than the other. And these weighted graphs, which we've talked about, have a number associated to their edges. Remember, a node is called a vertex in a graph, and the connection between two nodes is an edge. And depth first search doesn't really allow us to take into account these weights. We need something else. And in an interview, if somebody asks you this, your answer should either be Bellman-Ford or Dijkstra's algorithm that allow us to find the shortest path between two nodes of a weighted graph. Now, Bellman and Dijkstra are two real people that are academics, very, very smart academics that came up with their own algorithm to solve the shortest path problem of a weighted graph, such as Google Maps trying to figure out what's the closest way for you to get your burrito, for example. And just a side note, fun fact, this is Richard Bellman, and it's the same person that wrote about dynamic programming, which is an upcoming section in our course. Let's just say that both of these people are very, very smart. Now, both of these algorithms are quite complex, and it takes a lot of time to really get it and code it. So I will leave resources for you if you want to learn more about these algorithms, because in an interview, it's very, very rare that you'd ever have to code these algorithms. Most of the time, you just have to know that they exist and when to use them. So let's go over that. Bellman-Ford algorithm is very effective at solving the shortest path over Dijkstra's algorithm because it can accommodate negative weights. So if a weighted graph has negative weights or negative number, Bellman-Ford algorithm is going to be able to solve the shortest path problem, while Dijkstra won't be able to. Now, why would you ever use Dijkstra's then if Bellman-Ford algorithm can do better? Well, we won't get into the math of it all, but Bellman-Ford algorithm can take a long time to run in terms of complexity. And it's not the most efficient algorithm. The worst case for Bellman-Ford algorithm is usually a time complexity of O of n squared. So it's not very efficient. Dijkstra's algorithm, on the other hand, is a little bit faster than that and a little bit more efficient, with the downside that it can accommodate for negative weights between nodes. If an interviewer shows you this diagram and tells you, I want to find the shortest path from 0 to 4 on this weighted graph, you now know what you should say, right? What algorithm are you going to use? Are you going to use a breadth first search, Bellman-Ford algorithm, or Dijkstra's algorithm? The answer? Well, it should be Dijkstra's algorithm. There's no negative weights on this graph. It's a weighted graph, so Dijkstra's algorithm is going to solve that problem. Holy moly, another section done, and we're getting so close to the end. In this section, we learned about searching and traversal, some of the most popular and important algorithms. We learned about linear search and how it can be good for some cases, but not the most efficient because it has linear time, O of n. We also talked about binary search, where we're able to search through things at log of n, essentially skipping a lot of the nodes that we would need to search by dividing the tree in half. We then talked about how to traverse a tree in a graph, that is, to visit every single node in the most efficient way possible. We talked about depth first search, that goes in as deep as possible into a tree or a graph, and breadth first search, that goes level by level, searching or traversing a tree or a graph. And whether you realize it or not, we've completed a lot of this mind map that looked so intimidating at the beginning of this course. You see, now, when we look at arrays, for example, we understand that, well, when we need to search through an array, we can ask the question, hey, is it sorted? Because if it is, then yes, in that case, we should divide and conquer and arrange that array in a tree-like data structure so that we can do binary search and get a speed boost of O log n. Is the array not sorted? Well, no. Then it's actually more efficient to sort the array, even though it takes O of n log n, as we know over here, and then do a binary search after we sort it. And a lot of programs do that. Although it may seem time-consuming to do sorting and then searching, it is actually faster than perhaps doing a linear search over and over. But we can also complete this part of the graph, where we come to graphs and trees. When we do traversals, that is, try and visit a node in a tree or a graph, or all nodes in a tree or a graph, we know that it's going to take O of n. That is, we have to visit every node. It's going to be linear time. But there are ways to traverse these trees using breadth first search and depth first search. And we learned that breadth first search is great for the shortest path algorithms, while depth first search is really great at maze solving problems, or perhaps finding if a node even exists. And depth first search allow us to do in-order, post-order, and pre-order sorting. And we even coded this up all ourselves. And we learn how the code works using recursion with depth first search and also with breadth first search using both iterative and recursive using a queue data structure. Finally, we also learned a little bit about shortest path problems, such as the one that Google Maps would use, when there's weights between nodes in a graph, where we can use something like Bellman-Ford or Dijkstra's algorithm to solve a problem. Congratulations! This is your mind map, and you've covered every single thing on this map, with the exception of one, and that is this one right over here, dynamic programming. It's a short section to complete our overall mind map and get you interview ready. So I'll see you in the next section. Congratulations getting this far. You're almost there. Bye-bye. Welcome to our last section on algorithms. The last missing piece, and that is dynamic programming. Sounds very important, doesn't it? With this section, we're going to go over the very last piece of our mind map to complete our entire knowledge graph, so we're ready for interviews. It's this last little piece of dynamic programming, specifically memoization, that we're going to be talking about. But what is it? Dynamic programming is just an optimization technique. And here's the fun fact. Dynamic programming actually means nothing. It's completely garbage buzzword. And I'm not kidding here. I'll link to a funny article on how the name came to be. But dynamic programming, at the end of the day, is just an optimization technique using something called caching. If you have something that you can cache, well, then you can use dynamic programming. Now, we're going to get into the details of what that means throughout the next videos. But at a high level, dynamic programming is a way to solve problems by breaking it down into a collection of subproblems, solving each of those subproblems just once, and storing their solutions in case next time the same subproblem occurs. But let's get into that and understand what it means, how we can implement it to become better interviewers, better engineers, and better programmers. I'll see you in the next video. Bye-bye. In order to understand how dynamic programming works, we need to understand what caching means. Caching is a way to store values so you can use them later on. Ideally, you can think of caching as a backpack that you take to school. Instead of going all the way home when you need something like a pencil, you have a small box on your back that holds items that you need, so that when you go to school, you can just reuse them fast over and over. Now, that's a bit of a silly example. Caching is just a way for us to speed up programs and hold some piece of data in an easily accessible box. And memoization is a specific form of caching that we're going to be talking about because we use it a lot in dynamic programming. But instead of just talking about it, let's actually demonstrate it in code. The way we can cache things Well, let's imagine we have a function that says we want to add to 80. And this function takes a number, and all it does is return the value of n, that is the parameter we give it, and adds 80 to it. So that when we run the function add to 80, and let's say we put in 5, we get 85. Nice and simple, right? But if I run this function again, I'll have to go through this step again and add 80 to that answer. And if I do this again, do the same thing. I've ran the calculation 3 times. But what if this operation took a really, really long time? What if I had a console log here, and we can imagine that this operation takes multiple seconds. It takes a long time. Every time we run this function, we'll have to run long time 3 times and go through the step one by one, even though we've done the exact same calculation 3 times. Is there a way that we can optimize this? And this is where we can use caching and memoization. Let's improve the above function by doing something different. I'm going to create a new object called cache that's going to hold an empty object. We're also going to have a function that is now going to be called memoized, not memorized, memoized, add to 80. That takes a number. And inside here, we're going to do something a little bit different than the above. We're still going to add to 80, but we're going to do it in a special way. I'm going to say that if n is in cache, and this is a way to check if a property exists in an object in JavaScript. So it's similar to me doing cache.n to check for the property. This one just reads better, so I'm going to keep it like that. So if n exists in cache, so if we've cached it before, then simply return the cache.n or cache n. So return the cached value. But obviously it's empty the first time around, so this is not going to work. If there's nothing in the cache, which is the case the first time around, well, we have an else statement. And in here, we're going to have our cache n, which doesn't exist yet, and assign it n plus 80. So that after this, if we do something like memoized add to 85, it's going to say 5 plus 80. So in here, we're going to cache the property 5 to have a value of 85, which is what we're doing here. So that the next time around, we're doing something like this. We go through the if statement, find the fact that we've already calculated 5, and just do simple property access, which, as we know, is all of one time, is super fast with a hash table like this. Let's complete this example to show you how it works. I'm just simply going to return cache n, since we just filled it up here. And let's just have a console log here that does long time to see that we're doing the calculation that takes a long time. The first time I run this function, I get 85, and oops, I have the cache pre-filled, so it didn't calculate the long time. Let's try that again. Click run, long time. The first pass through, it went through here and did this calculation that hypothetically is going to take a really long time. Again, we're using a nice, easy example here, but you can imagine this being a calculation that takes a long time, many seconds. What if we do this again? We can console.log here to make sure that we capture these values. And we'll label them 1 and 2, just so we can distinguish them. So the first call and the second call. If I hit run, look at that. First time around, we call long time and we calculate to 85. But the second time around, because this value was in the cache, we didn't have to do this long calculation and we just returned it immediately. So what is memoization exactly? Well, memoization is a specific form of caching that involves caching the return value of a function, that is, the return value of this function, based on its parameters. And if the parameter of this function doesn't change like it is here, then it's memoized. That is, it uses the cache because it's calculated the same thing before with the same parameter, and it will return a cached version of the function. It's memoized. If the parameter changes, well, it's a different parameter that it's never seen before, so it's going to calculate both times different things. And I just noticed here that this shouldn't be 5, it should be n over here, so it's dynamic. There you go, that's better. So remember this, memoization is simply a way to remember a solution to a solved problem, so you don't have to calculate it again. Welcome back. I want to improve this function just a little bit. You see, ideally, we don't want to fill the cache in what we call the global scope. That is, to be living outside of this function. Ideally, it's good practice to have memory, or in this case, the cache, to live inside of this function, not polluting the global scope. And there's many ways to do this based on the language. In JavaScript, we can use something called closures. And this is what it would look like. And I'm showing you this because when we get to dynamic programming, you're going to see this pattern a lot. Luckily, with dynamic programming, the pattern is usually always the same. So once you learn this, then it becomes easier and easier. So the way we bring this inside of the function is to, well, bring it in like that. But the problem is now that every time we run this, we get long time each time because the cache gets reset every time the function gets called. So the cache becomes an empty object. To get around this, we can use closures in JavaScript. And we can return another function, so a function that returns another function. And in here, we'll pass the parameter n. And we'll have the logic inside of this function. That's it. And because of something called closure, we're able to access this cache inside of this child function. Now, this isn't a course about JavaScript, so you can read up on closure on your own. But this is just a way for us to avoid that global scope. So that this time around, we can do something like this. We can simply say const memoized equals memoized add to 80, and we'll run this function. And we can actually even remove the parameter from here so that we have flexibility. Let me show you. We have the memoized here, which hopefully I can spell, memoized, so that now this function, because I ran it, is going to return for me this function. Memoized equals this function. That's literally what memoized add to 80 returns. And I have access to this cache variable. So that in here, I can just say memoized 5 and memoized 6. If I hit run, I still get the same thing. But if I do 5 and 5 and I hit run, look at that. It's memoized. This function remembers that the parameter has not changed. It's the same parameter, and it's going to check the cache and say, I don't need to do all that silly calculation. I already have it. Here you go, just using a hash table. Here it is. And what we just learned here is really powerful because it allows us to be very efficient with our code. Something that we know interviewers love, companies love. And dynamic programming allows us to use what we know now about memoization to optimize our code. Let's find out more in the next video. Welcome back. I want to show you one last example. And this is probably the best example of why dynamic programming is so important. And as you remember, when I say dynamic programming, which sounds kind of confusing, just think of caching, of optimizing something using a cache. One of the best examples of why dynamic programming is so good is our good old friend Fibonacci sequence. We learned about this in our recursion section of the course, where the previous two numbers add up to the next number. So that 13 is 5 plus 8, 34 is 13 plus 21, and it keeps growing, keeps growing, keeps growing. And we learn how to calculate that, right? We're able to calculate the Fibonacci number quite easily. We had function Fibonacci, which is a really hard name to spell. I believe it's this way. And all we did was we said, using recursion, we had a base case of n is less than 2. In that case, we'll return n. Otherwise, we did some fun recursion. We return Fibonacci n minus 1 plus Fibonacci n minus 2. So that if I want to find the Fibonacci number at index of, let's say, 6, and I run this, and this should be n as in number. Let's run that again. I get 8 because 0, 1, 2, 3, 4, 5, 6 is 8. If I do 7, I should get 13. Awesome. This is something that we should be familiar with. But let me ask you a question. How efficient is this function? And we've talked about it before, right? It's not very efficient. If I have a variable here that says, let's call it calculations, which will equal to 0, and we're just going to increment this every time this function gets called. And because it's recursive, we know that it gets called a lot of times. If I do Fibonacci 7, how many calculations is that? That's 13 calculations. So 13 times that we ran through the Fibonacci function. What if I increase that to 8? 21. Okay, what about 9? 34. What about 10? 55. All right, it's increasing pretty fast. What if I do 12? 144 calculations. Just to get the 12th index. Wow. What if I do 15? 610 calculations. What about 20? Holy moly. Over 6,000 calculations. And just for fun, what if I do 25? Oh boy. All right, one last time just because we're having fun. 30. All right, that's a lot of calculations. And by the way, if you want your browser to crash, just type in 50 or 60 and see what happens there. Regardless, if we look at this, is pretty terrible. Just to calculate the 30th number or index of a Fibonacci sequence takes that many steps, that many calculations. That is a lot. It's not very efficient. And we know this, right? Because in our recursion section, we talked about how that Fibonacci sequence and the way we're running the function is O of 2 to the power of n. Really, really bad time complexity. As we saw, just doing 30 calculations takes a lot of steps. And remember, with recursion, we're adding every nested function call adds to the stack, which increases our memory complexity. And we would never want to do an operation that costs this much in real life. So how can we make it more efficient? Can we make it more efficient? I mean, if you wrote that function, is your boss going to fire you because it scales so horribly? I mean, if your boss is horrible, maybe. But if you know dynamic programming, you can avoid this. Because what if I told you that we can do O of n with this function? Because with dynamic programming, we can. That's right. We can go from O of 2 to the power of n all the way down to O of n. Sounds like magic, doesn't it? And this is where we get to the next step of our dynamic programming. We can reduce the time and space complexity of our algorithm by using memoization. And we can do this because the solution to each subproblem is what we call optimal. That means we do a lot of problems repeatedly that are the same. In the next video, we're going to explain this concept and see how we can use memoization. I'll see you in that one. Bye-bye. Welcome back. If we take a look at our Fibonacci function that we created, this is what we're doing. If I was looking for a Fibonacci number of 7 using recursion, well, we'd have to run all these calculations recursively and all of these as well. And you can see here what's happening, right? Look where we're calculating Fibonacci of 1. We have this function running 1, 2, 3, 4, 5 times, calculating the same thing. What about Fibonacci of 2? Again, look at all these calculations that are being repeated. What about 3? And you see here where the triangles are overlapping, where we're calculating 3 over where we calculated Fib 2 and Fibonacci of 1 as well. And then if we keep going to Fibonacci number of 4, there again, repeated tasks. Triangles over triangles. And then finally, Fibonacci of 6 or 5, we see that once again, we just have more repeated calculations. This does not look efficient, does it? And that's what we saw in the previous video. This is what we're doing with our calculations. But if you notice here, with dynamic programming, we can optimize this and use memoization to say, hey, calculate Fibonacci of 7, go recursively down to 6, to 5, to 4, to 3, to 2, and also to 1. And now, as we go back, remember, as we start to return the statements, and we go to Fib of 2, or Fib of 3, or Fib of 4, because we've already calculated these numbers, we can actually return a memoized version so that all these calculations are no longer needed. Why? Because 2, 3, 4, and 5, every time we ask for it, in this case, we've already calculated on the left-hand side. So we can use the cached or memoized version so that these we can just ask the memoized function to just give for us. We avoid all these calculations. Look how simple that looks. And I'm going to show you in the next video how we actually implement this with the Fibonacci sequence. But to demonstrate to you that this is not only just this problem that we can use dynamic programming on, I have a set of rules. One is that you can think of dynamic programming as combining divide and conquer, what we did with the tree-like structure of Fibonacci number, where we use recursion, and using reuse, that is caching and memoization, with recursion to get savings in performance and use dynamic programming. And these are the steps that I like to follow to see if a problem can use dynamic programming to optimize it. We first ask, can the problem be divided into subproblems? That is it a tree-like structure where each problem is broken down into smaller problems, into smaller problems, into smaller problems, which usually indicates a recursive solution? Again, something that we're very familiar with from our previous videos. And now the third question is really important because you can have tree-like structures that don't have repetitive subproblems. But if these subproblems are repetitive, that is, we're doing the same calculation over and over in these subproblems, well, if the answer is yes, then we can memoize these subproblems. And once we do that, we see tremendous benefits. And these benefits are used all over computer science to improve performance. So that the fifth step should be to demand a raise from your boss if you've implemented this because you've just saved so many calculations, so much time complexity. I want you to think like this. Instead of being intimidated by the confusing name that is dynamic programming, you just need to know when a problem can use this technique. And I'll leave some problems for you after this section to practice on. But you want to just follow this pattern. When a problem has solutions composed of solutions to the same problem with smaller and smaller inputs, each subproblem is solved only once, and the result of each subproblem is stored in a table like a cache, such as a hash table, like we've done in the previous video, for future reference. We can use this table to obtain the original solution of a repeated problem. Enough talk. I think it's time for us to implement our own memoization with Fibonacci number. If you want to challenge yourself, go ahead and see if you can code it yourself. Otherwise, in the next video, I'm going to show you how to improve our terrible performing Fibonacci function into O of n. I'll see you in that one. Bye-bye. Welcome back. Let's use dynamic programming and memoization to improve this function. Just like we did when we learned about memoization, this is fairly simple. Let's remove this for now. I'll keep this at the top. And in here, create a new function. We'll call it Fibonacci master. This function will have a cache, a hash table, or an object to store our pre-calculated answers. And if you remember, because we want to make sure that we don't reset this every time we run this function, we're going to return another function inside here, again using closures in JavaScript. And in other languages, you might have to use different techniques. And in here, we can just have a function. We can name it whatever. Let's call it fib. That takes n. That is the number we give it. And inside here, well, we do something very similar to the above, except we're going to check the cache first. We're going to say if n is in cache, just like we did in the memoization videos, and we're going to check if the cache exists. And if it does, we're going to return cache n. The first time around, this is going to be empty, so it's not going to work. It's going to go into the else condition. And in here, we have two conditions, just like we do up here. If n is less than 2, then we need to return n, just like we did above over here. Otherwise, we run our sequence. So we do fib of n minus 1 plus fib of n minus 2. But we want to store this value in our cache. So we're going to say cache n is going to equal the result of this. And finally, we want to return this value because we are using recursion here, and return cache of n, which we've just set. And that's it. That wasn't that hard, right? I mean, we have a few extra steps, but all we did was just add the result to our hash table. So that now, if I do const, let's say, faster fib, is going to equal to Fibonacci master. Remember the first time around, we're going to run this function and create the cache variable. Whoops, let's try that again. And create the cache variable, and it's going to just return this function. So it's similar to just saying like that, faster fib equals this function now. Except that now we have access to the cache variable. So that now I can console.log, and let's call this DP for dynamic programming, and we'll say faster fib and give it, let's say, 10. If I run this, I get 55. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 55. That's pretty good. But let's do something fun here to see if it works. This calculations tally that we used in Fibonacci number, let's move it to the Fibonacci master. Or instead of here, down in this function, because this is the one that we were cursing over. And let's see how many times this calculation happens. If I run this, oh, and we need to console log these calculations. So at the bottom over here, let's have a console.log. And we'll say we did calculations, just like that. So that if I run this, we see that we did 19 calculations with the Fibonacci master when we entered 10. Versus if we move back calculations up to here, to our old version, oh, and we actually have to run this function. So in here, let's just have console log so we can have everything clean. We'll say console.log. This will be called slow, and it'll be called, what was it? Fibonacci. So we'll just do our original function, Fibonacci, with 10. So let's see and run. We got the same answers, 55, but it took us 177 calculations to get to 10. Holy moly. So 19 versus 177 calculations. And if we do 20 here, well, we have that many calculations. And actually, let's just do 35. See if that's possible. Let's see 35. There you go. Look how many calculations we had to do. Versus if I do 35 with our memoized function, move the calculations in here. And we run this. 69 calculations. That's it. Instead of before, where if I entered Fibonacci 50 here, it would actually crash the browser because we would do so many calculations. With this one, I can do Fibonacci 100. And I have no problem. Look how fast it calculated that. That's pretty amazing. It only did 199 calculation. I hope you see the power of dynamic programming. And it's not that hard, right? All you need is to remember this pattern. And if there's any repeated calculation, to just memoize the result of a function. So that if the parameter is the same, we check in the cache first for the result. But let's talk about space and time complexity here. This, well, because we're only doing the necessary calculation, in this case, all our calculations, well, are n, right? We do 1, 2, 3, 4, 5, 6, 7 calculations versus all the ones that we did before. So that our time complexity for this one is O of n. Versus with this one, that was O of 2 to the power of n. Just like that, we made huge savings. the one drawback is that, well, we increased the space complexity, right? I mean, with the first Fibonacci number, we had to add functions to the stack. And these functions, the deeper it is, we added to the stack. But once we got to the bottom, we popped off the stack so that the stack was as deep as the tree. But with the memoized version, we also have this new variable, this cache hash table that we have to store our memory in. But as we know, we sometimes need to trade off space complexity for better time complexity. And this is what we're doing in this case. And in this case, the time complexity savings are very, very large. All right, I hope I got you excited about dynamic programming. It's very interesting and not as overwhelming as you think, right? I'll leave a couple of problems for you to do to get used to dynamic programming, but I recommend that you take the code that I'll leave here for you and you can just grab it from resources and play around with it. Otherwise, I'll see you in the next video. Bye-bye. Welcome back. In this section, we finalized our understanding of algorithms with dynamic programming. And we've completed all of this. And now, the very last piece of the puzzle is complete. Dynamic programming, and specifically using memoization to optimize our problems, completes our entire diagram, our mind map of how to master the interview. So what did we learn? We learned that with dynamic programming, we can identify these types of problems by first seeing, hey, is there a problem that can be divided into subproblems of smaller pieces, where most likely you're using recursion. If you're using recursion, then ask yourself, are there any repetitive subproblems or tasks that I'm doing over and over? In that case, we can memoize these subproblems so we don't constantly recalculate things and use this idea of dynamic programming so that we get a nice raise from our boss because we just made the code so efficient. Now, memoization is a common strategy for dynamic programming problems, which are problems that I just described here, such as the Fibonacci problem. There is one other way of incorporating dynamic programming, and it's called bottom-up approach. And we won't focus too much on it, but I want to show you quickly how it might look like. In our case, there's actually a third way to solve this problem. And the way to do it is, well, it's actually fairly simple. We can do Fibonacci master 2. And in this function, we'll have the answer, which will be the list of our Fibonacci sequence, which is right up here. And we're going to pre-fill it with 0 and 1. And then from there, all we do is a for loop and say let I equal to 2, because we're now starting at the second index. I is less than or equal to the number n. And we'll increment I. And then finally, we will say answer.push. And we'll push to the next item in this stack the results of the first and the second. So I minus 2 plus answer I minus 1. And then we can just return answer dot pop, which will give us the very last item in the list according to what index we're looking for. So that if I run this, and call it DP2, I should still get, and I have to make sure that I pass in, let's say 100. If I run this, there you go, we get both of the same results. And this type of approach avoids recursion. Some would say is not as clean, not as easy to understand, while others will say, no, this makes a lot more sense. It really depends on your preference. And This type of solution is called bottom up because you start from the simplest solution from the bottom and slowly work your way up higher and higher towards more complex problems. But these types of problems, although easier to see, are harder to figure out when to use. So I prefer the top-down memorization approach of using this. But I just want to show you that there is another way of doing things. And in an interview, it's very rare that you're going to be asked to implement both methods. But at the end of it all, I hope you see the power of dynamic programming, this simple concept of saving ourselves a lot of trouble thinking about how our programs run and how we can optimize it so that we don't do any repeated tasks. If you're able to notice these things, then you are a great engineer. I'll see you in the next one. Bye-bye. Hello and welcome back. If you've gotten through the intense coding section where we learned about data structures and algorithms, well, good job. The good news is that the hard part is over. The bad news is that, well, you're not going to get any job you want because coding is just part of a job interview. And as you know, you have the technical side and also the non-technical questions. And depending on who you are, you might find one easier than the other. And when we say non-technical questions, those are the questions asked in an interview by the interviewer to see whether they want to work with you, whether you'd be a good fit in the company, and to make sure that you're not only just good at coding, because you have to be good at working well with others. In this section, we're going to tackle this problem. How do we succeed in a non-technical interview when we get asked what we call behavioral questions? Let's have a look at what we're going to talk about. In this section, we're going to talk about what we're going to do during the interview. And we're going to create an overall strategy so that we're as successful as possible, just like we did with the technical part. We're going to talk about specific questions and how to answer them. And the good news is that most of these questions are the same. They may sound different at different companies and they might tweak it a little bit, but the overall answers are pretty much the same. So once you've gone through a couple of them, it actually becomes easier and easier. And all these questions can just be given with the same answer. So all your non-technical interviews pretty much sound the same. So let's just perfect that. We're going to talk about how to answer questions like, tell me about a problem you solved. Why do you want to work for us? What kind of questions to ask the interviewer at the end of the interview? The question that we always get asked at the beginning of the interview, which is, tell me about yourself. How do we answer that? What is our biggest weakness? And then we're also going to talk about what to do after the interview to maximize our success, and also a little fun secret weapon section where I'm going to talk about some of the things that we can use to impress the interviewer. It's going to be a fun section. We're going to take a break from coding. So if your brain is a bit of a mush after the coding section, well, you can just take it easy, sit on the couch, press play, and hopefully I don't bore you too much. So I'll see you in the next video. Bye-bye. Welcome back. Let's get into this section. And the very first thing I want to talk about is mindset. You see, the biggest mistake that we make going into an interview is that, well, thinking that this is your only chance. The way you walk into an interview is to walk in knowing that you have many other opportunities. This is just one of them. It's not do or die. It's not pass or fail. If this interview goes wrong and you don't get the job, your life isn't over. So first and foremost, treat everything as a learning experience. And what I mean by that is you go into the interview, whether it's a phone interview or an on-site interview, not expecting a job, not hoping for a job. Don't hope for anything at all. Just go to learn, to see where your weaknesses are, to learn about a company, and as with anything, as if you're running code, to check how good your code is. You just want to see how good you are at interviews. So that's the key. This is not your only chance. And if you go into that already, you're going to be less nervous. You're going to be more comfortable. It's going to help you out a lot. I know it's silly. I know it's one of those things that we all know, but really do that. Don't go into an interview nervous and thinking that, you know what, if I don't get this, then I'm not good enough. No, this is just another practice, another day at the office, you just trying to get to where you want to be next. Now, what about when you actually go into the interview for the first time? And this is where interviewing is very similar to dating. Your interviewer is more likely to be excited about interviewing you if you're excited as well. Because sometimes interviewers are people from human resources that do this every single day, or it could be other coders that are just taking time out of their day to interview you. So you want to make this exciting and fun for them. It's not all about you, it's also about them as well. And they want to see if they want to work with you. This is a little trick that it sounds silly, but it really, really does work. Your goal is to enter the room with a lot of energy, being happy, excited to be there. And this is a classic psychological technique where humans, when we interact with each other, we match each other's energy and energy level. So if you're excited, if you're walking in there with a big smile, ready to get the interview going, it's also going to jolt the interviewer to say, all right, let's do this, let's have fun, instead of just going there nervous and scary, because the interviewer is going to match your energy. So this is the trick. Before you open that door, say to yourself, I'm about to go meet a really good friend, like you've known them for years. And by acting like that, you're going to make the interviewer like you more. Again, it sounds silly, but it is a proven psychological technique. Not only that, but excitement is a signal that you actually want this job. So again, you're walking in, about to meet a best friend, and you're trying to make the interviewer's day, not bore them to death. And an interviewer wants to ask or answer 3 questions during this interview. The first one we know. Can you do the job? Do you have the coding skills necessary? Do you actually have the skills necessary? But this isn't the only question. You also have, well, can I work with you? Is this the type of person that I want to be coworkers with? Are they going to be fun to be around? And this is a very important question that gets answered during these non-technical questions. And then the third one is, are you going to improve? Because most of the times when you get hired as a developer, you're not going to be 100% perfect match for them. On your first day, on your first week, the first month, you're learning on the job and learning their ways, how their code bases work, how their best practices works, and you're constantly improving. And they're looking for people that can adapt quickly and learn, and a year from now become a really valuable asset. The first question, can you do the job? We're prepared for that because we just finished the coding section. We know how to answer difficult technical questions. But these other 2, we haven't really talked about them. And again, that's what we're going to cover here. We're going to have the interviewer say yes to both of these last 2 questions. This is what we call behavioral question. Can I work with this person? Is this person going to be fun to work with? And are they the type of person that's constantly improving, that's going to become better and better? How do we do this? Well, for the rest of the section, I want you to keep in mind these 4 figures, what I call the 4 heroes. And I know it's silly, it's going to be a little cartoonish, but this way, hopefully you remember this. You see, before you enter the interview, you have to have somewhere between 2 to 4 stories prepared that I call the 4 heroes. And it has to demonstrate to the interviewer that you have these 4 hero qualities that they're looking for. The first one is technical. You want to have a story prepared about your past experience. Maybe you worked on a really difficult project or a personal project that is going to impress the interviewer. A story just for yourself that you know a lot about because you've worked on it, and something that shows the interviewer as soon as you tell the story that, oh, this person is really technical and knows their stuff. So that's when we build that 1 to 2 big project in our portfolio that we talked about at the beginning of the course. That's when this comes in. So you want to demonstrate that you're very technical and smart. That's the first hero. The second one, success. And this hero story shows you that you're a successful person. If you built something what did you do? Did you maybe start a little app that turned out to be quite successful and it got a lot of users? Maybe at your past job, you got promoted to a senior level position. You want to have some sort of story that shows you that you're a successful person, not a person that never succeeds in any job. The next one is leadership. Are you the type of person that takes charge, doesn't get told what to do all the time, and can be left on their own? Do you have leadership qualities? And then the last one is challenge. And challenge is they want to hear a story of you going through some really challenging things, maybe a challenging technical problem that you had on a project and how you overcame it. Because you're a type of person that when presented with something that is really difficult, that has no clear solution, you can overcome it. When left alone, you can overcome any challenge. And these 4 stories are going to be specific to you. So I can't really give you a story to tell the interviewer. Look in your past experiences, and I guarantee you, no matter what level of experience you have, you'll have some stories from your past. It could be from work, it could be from projects, it could be from other things, where you're able to demonstrate these 4 heroes. The rest of this section, the answers we're going to give, what we're going to talk about, are all going to demonstrate these 4 heroes. We're not going to say to the interviewer, oh, I'm a very successful person because I did this. No, we're going to tell these stories that we have. Remember, 2 to 4 stories that demonstrate these hero values. And we're going to tell these stories, and the interviewer is going to get that we have these 4 qualities, these 4 heroes, just through the stories. And if you have these stories prepared before the interview, well then you can always, depending on what question you get asked, you can always answer these questions with some sort of these stories that you have, because these stories are already prepared for you. This is where I say that all non-technical interviews sound the same, because you have these stories prepared and you just change them up a bit to answer the specific question, but deep down inside, you're just demonstrating these qualities. Remember, these qualities are the qualities that we have to answer the last 2 questions. And that is, can I work with this person? And are you going to improve? So let's get into it and answer some questions that we might get asked in an interview. I'll see you in the next one. Bye-bye. A question that you're going to get asked at every interview that you do. Tell me about yourself. What should you say? And I'm going to leave this on the screen so you can just read it on your own. But this is something that should be already prepared and you're ready to answer and really nail it. How can we answer this question successfully? You see, this is the chance for you to steer the conversation in the direction that you want, in the prepared stories of the 4 heroes that you want. Remember, you're going to direct the rest of the conversation after they ask you this question to what you want them to ask you so you can shine. Some of the key takeaways here. You want to answer this question in about a minute. If you go too long into it, well, the interviewer is going to get bored. And if you go too short, then they don't get enough of a chance to get to know you. The key here is for you to tell your hero's journey. How you went from very little skill to somebody that they want to hire. Think of it like a movie. You want to talk about your triggers of success. Within this minute, you want to demonstrate that you're a successful person. You also want to slightly discuss maybe your past projects, your past companies, so that you get asked questions about these projects or past companies by the interviewer. Because keep in mind, the interviewer is going to ask follow-up questions based on this. And when you talk about yourself, maybe it's interesting that you were an origami master 5 years ago, but it might not matter to the interviewer. So make sure that your stories, your hero's journey is relevant to the job. And you mention some of the skills that you're going to be working with at this job. Within this minute, you want to demonstrate that they will be extremely lucky to have you and how everything you've done in the past makes this a perfect role for you. And keep in mind that an interviewer may not have even looked at your resume. So have a story prepared. Something difficult you did and what you did to solve that and what impact it had. You don't need to talk about your life story, how you went to elementary school, then high school. Just keep it short and to the point, but make sure you stand out from the crowd. Everybody might be able to code in JavaScript, but what did you do that makes you stand out? And that's something that you're going to have to answer on your own. Keep in mind that this type of question, there's different variations on it. Some people ask, walk me through your resume, or why are you leaving your current job, or many other variations. Essentially, they just want to hear the story of why you're here. And as an example, here's what I would say if, let's say, you have zero experience, and you just taught yourself to code, and this is your first job interview. You can say something along the lines of, well, I got really interested in coding a couple of years back when I would start this small little side businesses, and I would hire developers and designers to build a website or an app for me. And it was always a black box where I would pay this developer money and they'll come back with a product that I was never fully satisfied for. So I started teaching myself how to code because I wanted to know how this black box works. And the more I learned, I became really interested, really engulfed in the programming landscape. And I just started consuming as much information as I can, practicing as much as I can. I started building projects, and then this is where you can talk about some of your big portfolio projects. And all of a sudden, I started writing blog posts about technical subjects that got received very well. And I guess what I'm trying to say is that through these projects and through these posts, every day I'm becoming better and better as a coder to the point that now I feel very confident in being able to be a valuable asset to your team, not just now, but even a year from now, where I expect my skills to exponentially grow. And this is just an example that I came up with at the top of my head, but you see here how I touched on all 3 points. Shows that I'm successful, that I've had past businesses in the past, how I've taught myself how to code because of an interest that I had. So I'm the type of person who's a go-getter. I also mentioned a few things I want to get asked, such as blog posts I've written, maybe projects I've worked on, my personal projects that I've put into my portfolio. And I also talked about skills relevant to the job. Maybe this was a position related to web development or building an app. And this is something you can tweak. But the key thing is to have this prepared. And remember, you want to stand out. Don't say things that all the other developers are saying or programmers are saying. If you did something amazing in your life, even if it isn't coding related, try to work it into the interview. And that way you'll be more memorable. And this is going to set the stage for the rest of the interview. So good luck out there. And I'll see you in the next video. Bye-bye. This is another question that gets asked a lot. Why us? Why do you want to work for us? Why did you choose our company? A question that gets asked every time. And any question that gets asked every time, you should be very prepared for. This is where you shine. And you really have an answer that blows them out of the water. The key here is to make the interviewer feel special. Make them feel that this is your top choice and that this is where you see a long career for yourself. They don't want to hire somebody that's going to be there just for a year. They want somebody who really wants this job and is willing to dedicate years of their life growing with the company. So make them feel special. Make the interviewer feel that you really, really like this company. You admire this company. And also that you respect the fact that they work there. This is the classic question where you can give a very generic answer that everybody says and you won't stand out. And remember, interviewing is all about standing out, not doing what everybody else does. So a typical answer to a question like this, well, a really bad answer to a question like this will be something along the lines of, well, I just saw you guys on LinkedIn and I needed a job to make money. That is a terrible answer. So never say that. A better answer is something along the lines of, Well, I've been researching your company for a while, and I noticed that you're doing some work on X. And I myself have done some work in the past similar to this, and this is what I learned about it. And then you can go on with that, and then you can say something along the lines of, and I think the problem of X is really interesting, and I think it's something that I can add value to, but also learn and become better at. And again, this is just an example, but the idea here is that you're going to blow them out of the water. They expect you to give a generic answer, but instead, you talk about a specific problem. You talk about the fact that you did your research. Perhaps you talk to other developers at that company through LinkedIn, or you read one of their recent blog posts and you understand what kind of problems they're trying to solve. You answer this question by demonstrating that you have those skills. You mention some of the key words that they have in the job description, but also demonstrate that you're not like the rest that just wants a job and they're applying to a ton of companies. Tell them that you specifically searched companies and found this company interesting because of the type of work they do. It shows that you want to grow, and it also demonstrates that you'd be great for this job because you've worked with some of their problems in the past. And this might remind you of, yes, the 4 heroes. You talk about the technical aspects and how you worked on similar things that they're looking for. It shows that you're the type of person who's successful because, well, you're actually going out and researching and not just applying to companies blindly and waiting for any company to accept you. It also demonstrates leadership because you went out on your own and read their blog posts, talked to their developers to make sure that you understand what the company's needs are. And then it also talks about challenge, how you worked on similar problems and you overcame them, or you think you can help out. And by this point, you should start to see a pattern. We're always trying to use the 4 heroes. We're always trying to stand out. And we're always trying to be the best version of ourselves to the interviewer. Now, before I end this video, I want to add a quick note here. And that is, part of the question might come with the follow-up question by the interviewer, which is, why did you leave your job? Why do you want to work for us? Why is your last job not good enough for you that you want to move? Everybody has different answers here. But the one thing that you want to be careful of is no negativity. They don't want to hear you complain about your coworkers, your boss, the ugly code base that your last company had. Be as positive as possible. Just say that you want to grow, you want more challenge, you want to work with people that are really smart, like they have at this company. No negativity, be as positive as possible, and show how you just want to grow. You just want to learn from the best, work with the best, and you are the type of person that can be put in any situation to succeed. And at this moment, this company is your answer. I'll see you in the next one. Bye-bye. Welcome back. Let's talk about another question that gets asked a lot in interviews. Tell me about a problem that you had and how you overcame it, or how you solved it. Again, a very common question. How do you answer this? Well, we should know this by now. This should be prepared. We should be ready when they ask this question, or any variation of this type of question. Ideally, you have a big project from a past company that you worked with, or a personal project that you can answer this with. Again, going back to our portfolio and how we want to have 1 to 2 big projects, so we can answer questions like these and also impress the interviewer. Now, with these type of questions, we want to use something called the SAR method, S-A-R method. That is situation, action, and result. When asked this question, we start off with the situation. We tell the interviewer, this is how the project was, this is the problem that we had. This is the situation. The second part is the action. What did you do to solve that situation? I did this. I wrote a piece of software. What did you do? How did you try and solve? And then the result is what happened after you took that action. The number of users increased. the performance of the website improved. So SAR, situation, action, result. This shows exactly what the problem is, what you did with the problem, and how you solved it. And you see over here the second point. We want to have metrics and numbers. If you're able to give numbers to the interviewer, it sounds impressive. If I say, I improved the performance of a website, or I increased the number of users, that doesn't sound impressive, versus saying something like, the website performance improved by 50%, or we increased our monthly active users by 30%. Again, something that you can prepare ahead of time in your stories. This is why when I talked about the portfolios, we want to focus on big projects versus many small projects. Because when you get asked this question and your problem is that you had a difficult time building a to-do list app or a small little app, it's not going to sound impressive. That's what everybody else does. Instead, talk about a real problem. And that's something that we've built in past courses where we talked about difficult problems such as caching, scaling, performance, security. And these three over here, scaling, performance, security, are really, really good things to talk about. If you're able to use one of these, of how you improve security, how you improved performance, how you improved scaling, it's going to be really impressive because all companies have these problems and they want people that can solve these type of problems. You have to be careful here. You can't just make up stuff or say things that you cannot back up. Expect that once you answer this question, the interviewer is going to ask you more details about it. So if you improved caching in the app to improve performance, you better be sure that you're going to get asked how you did it in more detail. So be able to answer those. But again, with enough preparation, this should be fairly easy to you. As a side note, if this problem happened to be with maybe a teammate or your work team wasn't performing well, don't be negative. Again, never place blame on clients or coworkers or bosses. Just simply state the problem and say how you helped solve it. People don't really want to work with complainers. They want to work with people that just get to work, solve problems, and move on. Keep in mind, don't be robotic when answering questions. Be human. And a good way to think about this is if you saw yourself on TV answering this question, will you like yourself? And that's really it. So go out there, have this question prepared because you're for sure going to get asked this question. I'll see you in the next video. Okay, I lied. There's one last thing, and that is you're going to get a variation of this question, such as tell me about an interesting project you've worked on. And they're very similar. The goal here is to talk about an impressive project to wow the interviewer and tell them how A, you're different because you're building these interesting things, but also how you've worked with what the company is looking for in the past. So you've worked with JavaScript, you've worked with C#, you've worked with C++. Whenever you're talking about a project, about a problem you solved, you always want to bring it back to what the company right now is looking for. Because at the end of the day, that's what they care about. They care about, can you solve the problems? So again, make sure you stand out and make sure you're related to the job. I'll see you in the next one. Bye-bye. All right, we're on a roll here, so let's just keep going through a few more questions here. What is your biggest weakness? How would you answer this? Well, here's the thing. With these questions, you better not give something silly like, I work too hard, or my biggest weakness is that I care too much about my coworkers. First of all, people can really see through that and label you as fake or a liar. But again, every question should be something that makes you stand out, that makes the interviewer say, wow, I want to work with this person. So how can we twist this around to something that the interviewer is going to say, yep, this person should be hired for this company? It's very simple here. One is you need a real answer. Again, no silly answers of how great you are. Be honest. Say something that you have as a real weakness, but the key is you have to show how you overcame it, how you improved it. So Don't say, I'm too passionate. Maybe say something along the lines of, sometimes when there's a problem, I get straight into coding without really thinking about the problem. And as I'm typing, I realize that perhaps I should have waited, planned out how I should write my code, how it should be structured, what problem am I really solving before I start just coding it. So lately, I've taken the time to make sure that I write pseudocode first, just commenting out the steps that I want to take, what my assumptions are, what my inputs are, and from there, write out the steps that I want my code to take before I actually dive into code. You see what I did there? I talked about my weakness, but somehow I turned it around to something that makes me a great candidate. Somebody that has improved from their past mistakes and now is working in a way that's ideal for a developer. That's it. There's not much to say here. Just be honest, but use this question as a way to, again, show how you're better than the rest, how you're a great candidate. I'll see you in the next one. Bye-bye. Do you have any question for me or for us? A question that always gets asked at the end of the interview. Once again, we should be prepared. What should we ask them? As always, the key here is to stand out. You want to make sure that these questions demonstrate how you're really interested in the company and how you've thought well about why you want to work here. The key points here are to focus on the interviewer. So use the word you, not I. You can perhaps say, I had a really good time at this interview. I do have a few questions for you. And then direct that attention to them. Because interviewers are humans too. And as humans, we like talking about ourselves. If throughout the entire interview, all they did was ask questions and all you did was answer questions, they're probably bored out of their mind, or at least not having as much time as if they were also got a chance to talk about themselves. So use that to your advantage. And ideally, if you're able to mention something that they mentioned throughout the interview, that also shows that you're paying attention and that you care, which is a big bonus. Listen to what they say about themselves at the beginning or during the interview, and bring it up later in the interview towards the end so that the question is tailored to them. Use their name and use what you know about them to ask a specific question. What are some of these questions that you should ask? Here are a couple lists of questions that I personally really like and I think are good questions to ask. And you only need to ask maybe 1, 2, or 3 questions, but you can pick your favorite. So here goes a couple of these. 1. What is the greatest mistake you made in the first month of the job? And what did you do? Again, you're interviewing them, but this allows them to talk about themselves. The second one, where do you see this company going in the next 3 years, next 5 years? I want to be here for a while, but you work here and you have better knowledge of the company than I do, and I would like to see where the company is headed. Again, a great question to show that you want to be here long term. But you also get to find out about long-term plans of the company. Why did you join this company? Again, ask them why they're here. Have you seen your skills grow in the past year? Another question is to perhaps ask them the one time that they messed up at the job and how it was handled by the company. And then finally, my favorite question, what they wish somebody told them when they just started the job at this company. That way they get to talk about their experience, and that way you also get to find out how the first week of the job will be. Now, all these questions are targeted towards the interviewer, but it shows that you actually care and that you have genuine questions and you're not just here to land a job, to make money, and that's it. Again, it makes you more human, less of a robot. It's really going to create a better bond with your interviewer. I'll see you in the next video. Bye-bye. So you've nailed your interview up until now. Everything's going well. The coding went well. Some of the questions that they asked, you were prepared for. You told your hero stories. Everything feels good. Or sometimes things don't work out as expected, and maybe you didn't do that well in your coding questions. Or they asked you a question that you weren't expecting in the non-technical questions. Well, never give up, first of all, because it's very rare that you have a perfect interview. Remember, you're not competing against 100% test score. You're competing against other candidates. Other candidates get asked questions too. There are ways that you can improve those odds and make sure that you still stand out, even if perhaps you didn't ace everything. And here I want to list out some of my, what I call secret weapons. Yes, a bit of a exaggerated name, but I think if you're able to work these into conversations, into questions, I think it will improve your chances of landing that job. Because what I'm about to show you are problems that I've noticed a lot in the workplace when it comes to programmers. There are a ton of really great programmers, but amongst them, there's always things that are common, that are problematic, perhaps not for us programmers, but for managers, bosses, CEOs. And by avoiding these common pitfalls, you can stand out and show that you're not a typical developer. So let's go over some of them. The first one is simplicity over complexity. It's very easy as a programmer to get into our own heads and complicate things and come up with really interesting solutions to problems that perhaps only we understand, or perhaps that only few smart coders might understand. But remember, code and problem solving is about solving problems for others. And as we know, code has to be maintainable, readable. You want to demonstrate that you're the type of programmer that emphasizes simplicity over complexity. Work that into your conversation. Work how when you worked on a project with team members, you wanted to make sure that the code was readable, that you didn't overcomplicate the problem just to appear smart or clever. Instead, you focused on readable code because you understood that working in a team means making sure that the code is readable and maintainable long after you've written it. This is a great thing to point out in an interview because it's rare for somebody to understand this with only a few years of experience. This is something that a lot of senior developers know, or senior programmers know. The next one is a famous quote that a lot of people must have heard by now. Premature optimization is the root of all evil. We always try to optimize our code, optimize performance, see what we can do better. But you have to work with your limited time. That is, based on how much time I have now, how many resources I have now. Is making a 1% improvement in performance worth it? If you're able to demonstrate to the interviewer that you're the type of person that understands the value of time and resources and money, and how you're able to work on things that matter, such as performance, which is a big one, without getting too obsessed with it, that's a good thing. And again, something that a lot of senior developers and programmers know. The next one is kind of related. You want to focus on overall goal and not be myopic. Now, what does myopic mean? Myopic means you're just very narrowly focused on one thing. So we get tasked with a problem, and all we care about is solving that problem. And we start to ignore some other things that might be important to the project. For example, a client might have a deadline that needs a product out the door and finished in a week. But you as a programmer focus on really good code, a really good performance. You ignore that request for 1 week and instead focus on really, really good code. And that's not necessarily a bad thing, but you have to understand the business consequences of what we do. And when you're working at a company or for yourself or freelancing, you want to look at the overall goal and not just focus on what you think is important. You have to understand what the needs are of the project and work with them. And again, if you're able to demonstrate this and work this into the conversation, such as saying something like, a client requested that we deliver a product before their big conference. I knew that that was a very important thing, so I set up a meeting with my team to make sure that that was our number one priority. and that we could always refactor code. And we actually dedicated time after the conference for a week where we refactor our code. But we made sure that the very first thing we did was to make sure that we're able to meet the deadline that the client wants, because the client provides the overall goal of the project. And a happy client means that we're able to continue working with them. Again, showing that you're not a typical developer that just gets given a task and that's all you focus on, that you understand the overall needs of your tasks. This is another very common one, especially amongst programmers like us, where we tend to like to complain about clients, ugly code, maybe coworkers that can get frustrating. First of all, that usually never helps, but it also creates a very toxic environment at the workplace. Nobody wants to work with somebody that complains all the time, that creates this negative energy. And if you're able to talk to your interviewer and how you're the type of person that is comfortable working with clients and that you don't like complaining or being negative about coworkers or bosses, well, that immediately makes you stand out because you're a pleasant person to work with. And that's a hard thing to put into a conversation in an interview, but there are ways of doing it, such as your past experiences where you may have demonstrated these values. And then finally, this is a big one, no ego. When we write code or when we program, when we solve problems, we take pride in our work. And when we submit something like a pull request or somebody checks our code and they make comments to it, we might feel a little bit hurt by these comments because we feel that we're not perfect, that we made mistakes. And a lot of tension can form in workplaces when this happens. It is a big problem for companies. But if you're the type of coder that likes getting feedback, that takes constructive criticism, and understands that there's no ego here, we work as a team, there's no individual, and that the overall goal of the company or project is what matters, and you're able to demonstrate that, that immediately is a big sell, or it makes you a very valuable developer. And if you're able to do these things all over here, that makes you really stand out. I can speak from experiences when hiring developers and working at some big companies that these are really rare. Having a developer that understands these and is comfortable with these points is very, very valuable. And you mostly only see these with senior developers. So this is your secret weapon. If you're able to work these into conversation, it's going to really give you those extra points with the interviewer. I'll see you in the next one. Bye-bye. Whew, you just finished the interview. It's all over, all that preparation, all that work that went into it. It's finally done. These are the final seconds of the interview. What do? Well, first off, you want to thank your recruiter or the interviewer, and you want to sound excited. Hopefully this won't be hard. You're actually excited about the job. But you made a good first impression when you walked into the door, and you also want to end on a good impression at the end too. Be very positive, be very energetic, and thank them for their time. If you're able to, you can also ask for specific feedback on your interview performance. Usually they won't say, but that never hurts to ask either. And you also want to ask them when you should expect to hear back from them, so that you have some sort of a timeline of when the decision is going to be made, whether to give you the job or to do another interview. Now, at the end of the interview, I like to prepare something called a closing statement. Most people get intimidated by interviews, and especially technical ones. However, the first and last impression are what most interviewers remember. So, at the end of the interview, no matter how well the interview has gone, whether you think you're not going to get the job or whether you aced it, you want to conclude with something that touches on all of these points. That is, you want to make a statement that doesn't use the word I, so you don't keep talking about yourself. You want to talk about the interviewer. You want to express how you're the ideal candidate, the best candidate for the job, but doing so without bragging. So what does that mean? Here's an example of what I would say if it was the end of the interview, and I want to essentially end off the interview on a good note. Thank you for your time. I'm sure you have lots of candidates to see, but I want to say one last thing. There are no shortages of developers for you to interview. However, there is a shortage of good talented, egoless developers with ambition to learn. It's not the ones that are unable to admit that they are wrong. The best developers aren't the ones that know the language inside and out, at the expense of having blinders. It is not the ones who are unable to admit they are wrong. I am not the most experienced developer that you may interview today. But the one thing that you can guarantee is that there is nobody that you will interview that will work as hard to develop his or her skill every day, play nicely with all the other developers of the company, and isn't so narrow-minded in problem solving that he or she isn't willing to try new and novel ideas. When you hire me, you will rest assured that you won't have to micromanage me. You don't have to extinguish fires. And in 1 year, I'll be one of your most valuable employees. I can guarantee that. I'm at a point in my career where I want to be surrounded by a team that I can grow with and be surrounded by smart people like yourself. And I've chosen this company specific for that reason. And you've probably had similar experiences in your career where one company allowed you to really have an impact and propel your career. I'm at this stage now, and I hope to be part of the team with you. So thank you for your time, and I hope to hear back soon from you. All right, that was it. Now, this may sound a little intense, but who would you hire? A developer that did pretty well at an interview and blends in well with all the other interviews that the interviewer has done? Or the developer who wanted it more than any others and really showed how much they want the job? Again, this depends on your personality, but the idea is that you want to finish the interview strong. And after the interview, you want to write perhaps an email afterwards to the people that interviewed you. You can thank them. If during the interview there are technical challenges that you weren't able to answer, you can actually reply to them that you have looked at the problem and you have now found a solution. And this is something that you can probably do easily by Googling. But this shows that even if you didn't solve the specific problem that they had, you have taken the time to actually solve it now. And in this thank you email, you just don't want to sound like a robot. Just nice and short, thank them for the time, show that you're interested in the position, and that you look forward to the next step. Now, if for some reason you haven't heard back by the time the deadline has passed, just message them again and let them know that you're waiting for a reply and will need to make a decision soon since you're interviewing at other companies, but wanted to make sure that you don't make a decision without knowing the situation at this company, since you really enjoyed the interview process here. And this is a bit of a psychological technique that we're going to talk about in the negotiation and offer section. But that's a nice thing to say in case you're just waiting around for an offer. Because remember, the more time you wait, the more people they're going to interview. So think about that. All right, now it's just a waiting game. Good job on the interview, and hopefully everything went well. I'll see you in the next one. Bye-bye. All right, and that's it for the interviewing in the non-technical questions. I know it's not the most exciting section. It's a lot of me just talking, but I hope you see a pattern here. Once you learn this, it becomes easy because you can use this technique over and over and over throughout your career at whatever interviews you want. That's the beauty of non-technical questions. They're generally the same and they'll stay the same for many more years to come. So once you become good at them, then you're all set. But let's just do a quick review of what we've learned. We first learned that you want to have a good mindset when going into an interview. You want to be confident, you want to be relaxed. You also want to realize you're using the interviewer's time. So don't make this a boring meeting for them. Bring the energy and have a two-way conversation with them. They don't want to be sitting with a scared, worried, timid interviewer with low energy that is quiet. Have conversation, be human, don't be a robot, and interact with the interviewer. In psychology, there's something called primacy effect. And that is, we remember the first and last impressions best. So when you enter the room, be energetic, be excited, make a good impression. And when you leave the interview, in the final minutes, also end on a strong note. Have a strong closing argument of why they should hire you. And keep in mind that we always want to have our 4 heroes, stories that include these 4 heroes in our answers. Because this is what interviewers are looking for. And keep in mind, just because you feel like you're having a bad interview, it doesn't necessarily mean that you're not going to get the job. You're not competing against the right answer. You're competing against other candidates who may struggle throughout the interview just like you. I also want to show you a neat little tool that may come in handy for you. This is a website that we're going to talk about in the offer and negotiation section, Glassdoor. And Glassdoors allow you to look at companies, what employers are saying about them. But they also have a new interviews section where you can actually search a company and see what sort of interviews they ask. So you can use this as a way to prepare and practice if the company is listed on this website. You see, in life, success comes to those who are able to stand out and do the extra step that 99% of the people aren't willing to do. It's why you're taking the course. Most people don't practice for interviews. If we look at this in this way, we notice a big factor when interviewing. On top of working on coding questions, data structures, and algorithms that we cover in this course, you should also work on parts that don't often get attention from people. These are the non-technical questions where people want to find out whether you can speak to people on your team. You can communicate with clients and customers and coworkers. Whether you're able to focus on prioritizing tasks and not getting stuck solving a problem. Whether you need hand-holding or you're able to be independent and solve problems on your own. Because at the end, the interview process asks one big question. If I hire you, will you make my life easier? That's it. If you're able to make somebody's life easier and offer a big value, then you're going to be hired. People want to hire developers and programmers that will help their business grow and saves them time. So be that candidate and be that person. I'll see you in the next section. Bye-bye. Welcome to the best part of landing a job. You've done all the coding exercises you can do. You've prepared for the interview. You've done the interview. You've answered all the questions. And now you wait. And hopefully you hear back with good news. But the game doesn't really end there. As a matter of fact, this is the fun part. This is what you worked for. And there's an easy, obvious way of going about it, which is not practicing and not learning how to handle offers or negotiation. Or a bit of a harder way where we learn how to do these things properly so that overall we're able to have higher salaries, work for better companies, and just overall be more satisfied with our jobs. So we're going to take some time in this section to learn these skills that again will allow you to grow a lot faster and be more satisfied with your jobs. Let's have a look at what we're going to talk about. In this section, we're going to talk about how to handle an offer. When after the interview, somebody says, "Hey, congratulations, we want to work with you. Here's your offer." What do? Do you just say yes? What about handling multiple offers? A lot of people don't talk about this, but when you're interviewing, most likely you're interviewing at a lot of companies. And most of the time, you're not just getting one offer, you're getting multiple ones. How does this work? And how can you actually use them to improve the actual offers that you get? We're going to talk about an important topic of handling rejection. We're all going to get rejected one day. I don't think I've ever met anybody who's been accepted to every single job that they've applied for. We're going to talk about getting a raise and how it's actually a lot simpler than you might think. And obviously, we're going to be talking about negotiation and some of the negotiation tactics and techniques that is going to help you throughout these other videos and other lessons to prepare you for the real world. So, lots to cover. It's going to be a fun one. Let's get started. Even the greatest of engineers sometimes get rejected. Just like in dating. Sometimes two of the greatest people in the world may not be the right fit for each other. Rejections don't really mean anything, especially when it comes to interviewing. Because nobody really cares about the rejection. It doesn't go on your resume. It doesn't go in your LinkedIn profile. It just disappears once you get rejected. You see, winners And people that are good at interviewing just get up after a rejection and go on and keep swinging. I'm using a baseball reference here. I hope people understand. So here's the fun fact. I myself got rejected from numerous jobs. Does that make me a bad coder? Does that make me a bad employee? I mean, maybe. But it also means that it wasn't the right fit for one another. It's probably good that they rejected me because I probably wouldn't have enjoyed working for them. Or I wouldn't have gotten the jobs that I had if I wasn't rejected by the previous ones. You see, rejections are never a predictor of success. 99 rejections and 1 offer is better than 2 rejections and no offer. So it's all a statistic game. All you need to do is go out and bat, go swing, get interviews, and no matter how many times you're rejected, all you need is that 1. And if you get more than 1, that's just a bonus. So when you get rejected, see if you can extract as much information or feedback as possible from the company. Tell them that you're constantly looking to improve and that you love some feedback. I mean, they already rejected you. What's the harm in asking? Might as well get some information out of it. And then finally, ask them when it would be okay to reapply if you're still interested down the road. You see, I know a few people who have been rejected by numerous companies and they just kept applying and eventually got hired. I actually know a person working at Google who did exactly that. So don't burn any bridges. Just ask them when you can apply again. Just remember, think about how much of our life we actually spend searching for jobs versus actually working. We actually don't spend a lot of time in our overall life applying to jobs, interviewing. So if you look at the grand scheme of things, don't be disappointed if you don't get hired within a week. You should spend time looking for jobs and opportunities because most likely you're going to be there for a long time. So you want to make it count. You also can't say that you're unhireable and get depressed or sad because you had a few rejections. Sometimes luck just plays a role in interviewing. So just don't take it personally. It's okay to fail. I failed multiple times. Everybody fails. Sometimes you just have a bad day. It's not the end of the world if you fail, right? For companies, for example, they're more likely to say no than say yes because it is a big risk for them to hire somebody. You're going to start getting doubts in your mind about your abilities and your skills with all these rejections. However, like I said before, if you fail 10 times, try 10 times more. All you need is that one success. I promise you that if each day you're learning, you're getting better and better, your skills are improving, then one day you will get that offer. Most people just don't go out and keep batting. I'll see you in the next video. Bye-bye. Let's talk about negotiating. Now, first off, I'm no expert in negotiating or tactics. There are people who are better than me at this, and there's a lot of cultural standards and norms that may apply. So I'm going to tell you what has worked for me and also what I have seen work for others. Underneath it all, there are some few basic principles that can be applied. And this common theme and common tactics is something that will help you as well. But keep that in mind. Cultures do play a big role here. All right, let's get started. If you get asked, what salary do you want in an interview? What do you say? Think about this for a second. You can pause the video. What will be your answer when somebody asks you, what are your salary expectations? All right, you thought about it? This is what I would say. Well, I know that the average software developer in Silicon Valley, let's say I'm applying there, makes roughly $120,000 a year. So I think that's a good place for us to start. That was it. That's what I would say. Now, why is that? And this goes to my very first point. You don't want to end the conversation. You see what I did here? I didn't actually answer their question and say, well, I want $90,000 per year. All I did was do something called anchoring, where I tell them this is where we want our conversation to start. I want the conversation to start around the number 130,000 a year. And I'm not saying that this is what I want to get paid. This is just simply me starting our conversation so that we can talk about things. All I said was the average software engineer. In negotiation, especially when it comes to salary negotiation, you're going to want to give an actual number to end the conversation. Instead, you want to keep the conversation going by giving something like an industry average and make it clear that you're merely starting the negotiation here and not ending it. And that's how we start negotiating. Let's talk about the next point. We want to give reason for everything because we all know the problem with negotiating, right? If you say you want more salary or more vacation time, we kind of sound greedy. We don't want to sound greedy and that we're money hungry and that all we do is care about these numbers and ourselves. As we know, nobody really likes greedy people, right? As a matter of fact, this is the main reason people don't negotiate. They just don't want to offend people and seem mean and hungry just for money. Instead, you want to give a reason for everything. For example, if somebody gives you an offer, and this is something that we'll talk in later on videos, and says, hey, we're going to offer you $80,000 a year. What do you think? Are you in or are you out? Instead of saying, well, no, I need more time, maybe you could say something along the lines of, well, thank you very much for this offer. It's very generous and I'm very excited potentially working with your company. However, this is a big family decision and I'm looking to work at a company for many years. So I would like to discuss this with my wife or my partner and have some time to make sure that this is something we are both comfortable with. And you see what I did here? I just asked for more time or to not give an answer right away, perhaps over the phone, and instead speak to my partner. And all I did was give reason why I'm doing things. I'm not being selfish. I don't want more time just strictly for myself. This is something that I'm doing because I have somebody else that is involved in the decision. And by giving a reason like that, as an interviewer, that makes sense, right? I mean, the interviewer would be doing the same in your shoes. Let's talk about the next point. Always negotiate. I cannot emphasize this enough. See, negotiation is quite difficult and it is uncomfortable for most people. Actually, I've never met somebody that just loves negotiating. Maybe one or two. But negotiating is very tricky because it is very different between social dynamics and cultures and demographics. Appropriate advice for somebody in North America who's a white male may be different than somebody in a completely different location. There are so many factors at play here, and you know your culture best. But at the same time, don't use that as a reason to not negotiate. Being able to negotiate is present in all cultures. And you got to keep that in mind. You're never going to damage a relationship or have an offer revoked just by negotiating. I've never heard of anybody doing that or a company saying, no, we're taking the offer off the table because you're negotiating. So always negotiate. If you never ask, the answer is always no. And the larger the company, usually the more room they have to negotiate. I actually have a friend who works at a company where the same two developers that have the same job description, the same responsibilities, have a difference of $60,000 salary difference. One negotiated when they got hired, the other one didn't. And the other one is going to get raises and is going to increase, but it's going to take a lot longer for them to make up that $60,000 difference. Another point, and this is a very important one, is be positive. You have to realize that negotiating doesn't mean being mean. It's the exact opposite. You want to explore the situations that are available to you. And negotiations are win-win situations. If you go into a negotiation thinking that you have to screw over the other person, or there's always one person that wins and one person that loses, that's not a good way to negotiate. Negotiation is finding a balance between what two people want. And then finally, when negotiating, you have to have stakes. What does that mean? No, that doesn't mean delicious meat. Stakes means you have to have something on the line. If there's no risk and you knew for sure that the other side would sign a contract or accept the salary, then what incentive do they have to offer you more? If they know that you're desperate and this is the only job that you can get, well, there's zero chance of you negotiating with them. Your alternatives is what stakes are. By showing companies that you have other options, maybe you have multiple offers or another company that wants to hire you, you allow the person across the table who's negotiating with you to know that you're willing to walk away from the table without a deal. And that gives you a lot of power. So the best thing to allow you to negotiate is to have other options. You see, recruiters are always willing to negotiate if they want you, especially when they have a chance to lose you. Nothing makes a recruiter more angry or nervous than losing to a competitor company. And that's why you'll see people that have job offers from a big company like Amazon or Google that are able to get hired really easily at other companies like Microsoft, because those companies are competing with each other for some of the top developers or engineers. And if one wants a candidate, it means it's good enough for the other. And before I finish this video, I want to give another example of something that happened to me. I once got contacted by a book publisher, and they wanted me to co-author a book. And initially, they offered to pay a certain amount upfront before the book got published, and then I would get a percentage of the royalties. Instead of just accepting the offer, I messaged back and said that I'm very thankful for the opportunity and it sounds fantastic. However, based on the scope, time, and research that will take to write this book, I would like to discuss a higher upfront payment. I was very positive. I also told them that my time is valuable, so I showed them stakes that this is something that if I do it, it will take away from my other projects. I negotiated by telling them that I would like to ask for more. I gave a reason to the fact of why it deserves more upfront payment. And I kept the conversation going. And because of that, they came back with a higher upfront payment just by sending one email. But now let's talk about more detailed things, such as handling offers and getting raises. Using these techniques that we discussed, we're going to go into the next couple of videos and see how we can apply this to real life situations. I'll see you in that one. Bye-bye. Congratulations. You just received an offer from a company. You should be proud of yourself. Pat yourself on the back, take a couple of breaths, and now let's talk about what you should do next. You just received an offer. What is your response going to be? If you say, "Yep, this sounds great. Let's do it," you just ended the conversation. You just accepted and you've closed the door on any sort of negotiation. That's it. As a recruiter or an interviewer, their job is done. They hired you. But is there a better way? Remember, we don't want to end the conversation here. Instead, you might want to say something along the lines of this. "This sounds fantastic. I really thought this was a great fit when I met you and I interviewed you, and I'm really glad to see that we both agree and you see a good fit here. Right now, I'm talking to a few other companies, so I can't really speak to the full details of the offer until I'm done with the interviewing process and I'm closer to making a decision. But I'm sure that we can find something that works great for us, because I would really love to be part of your team and I had a great time interviewing and I could really see myself working there long term." You see what I did there? I kept the conversation going and I let them know that I'm interviewing at other companies, but I didn't seem very greedy. I instead said that I would love to work from them, but I want to make sure that I make the right decision based on the offers that I get. Remember, I was very positive. You want to be positive when handling an offer. You don't want to seem greedy or that you're just shopping around. And ideally, when you receive an offer, the first thing that you should try and do is to ask for more time to make your decision, especially if this is your first offer. Because ideally, you're not just interviewing at one company. You're interviewing at multiple companies. And ideally, if you're well prepared, like you have been in this course, then you're going to have a few more offers coming in. So time is the most valuable thing you can ask for here. The more time you have, the more time you have to have offers from different companies so you can make the right decision and pick the one or the company that has the best package for you. Now, you just received an offer. You just told them that you're very excited and you're waiting around for a few more things. And you also asked for time and you have an idea of when they want to give you a response. The next thing you want to do is, after you receive the offer, to let the other companies know. Again, if you're already interviewing at other companies, you now have a very powerful tool. You have stakes. You should be reaching out to all these companies that you haven't received an offer from to let them know that you've just received an offer. And you want to build a sense of urgency here, as if you have a timeline, a deadline where you have to say yes or no to an offer, so you would like to hear from these other companies as well. And this is a classic psychological technique. Remember, you're right now in the best part of interviewing, where the ball is in your court and you get to decide what company you want to work for. So you can actually send out an email like this to the other companies. Hello, name of company or person. I just wanted to let you know and give you an update on my interviewing process. I've just received an offer from another company. You can give the company name, which is quite strong. With that said, I'm really excited to potentially be working with your company. I had a really good time interviewing with you, and I really wanted to see if we can make things work. Since my timeline is now a little bit compressed with this new offer. Is there anything we can do to make the process go a little bit faster? And that's it. You've just let the other companies know that there's another offer. The other companies know that you're wanted and you're needed somewhere else. This creates a lot of social proof and also creates urgency, two psychological techniques that really, really help in negotiation. You now have stakes. You have to realize what a company's goals are. A company's goal is to hire someone who will become an effective employee and produce more value than the salary that they're paying them. What's going to cost to hire you? Companies try their best to figure out which candidates can produce that value. It's a risky business, right? And it's impossible to know for certain until they start working at the company and start producing results. But there are a few ways of companies finding out. That's what they interview for. That's why they have coding challenges or coding interviews. And another one is to see if somebody else wants them. If another company wants you, that means you succeeded through their interviewing process. When you're interviewing at big companies and you have an offer from a big company or a competitor, let's say you're interviewing at Microsoft and Google just made you an offer, you should definitely mention that, even the company name, to Google so that they know you're wanted. That creates a lot of social proof. So remember, no matter how useless or pointless you think this email to other companies may be, you want to send this signal to everybody, letting them know that a company wants you. It's a huge, powerful negotiation tool. Finally, always know when the deadline is to respond to an offer. Be honest with them and tell them that you're waiting on other offers from other companies. And you want to make sure that you make the right decision. They may want to try and rush you and tell them that you have to give them an answer by tomorrow. And you have to ask yourself, is that the type of place that you want to work? They should respect your time and the fact that you are trying to figure out the best option. When you're declining an offer, be polite and don't burn any bridges. Don't be mean, because you never know when you might see them down the road, or the person who is the recruiter there might move to a different company. And you never know when good relationships might take you further along down your career. So let's go over a few things. What should you do? The first thing is when you receive an offer, you should know exactly what salary you want. You have to go in there knowing what your value is, what you're willing to get paid. You need to make sure that you do your research on the average industry pay. You want to make sure that you're getting paid what the average professional in your industry is getting paid or above it. So you want to do your research and use websites like salary.com, glassdoor.com, payscale.com, or just simply Google it. And I'll leave resources for you to find this out after this video. The next, what value do you provide? You know what type of salary you want, but really ask this question and be able to answer yourself, what value are I going to provide for the company? What would you improve in the company? What type of traits do you have that make you a valuable hire? Think about how the company is going to drive value from you. And by doing this research beforehand, you're able to use this when negotiating your salary. And you can mention how you would provide value and why you deserve perhaps a higher salary or a higher offer than they've currently given. And then finally, you want to always go higher than what you wish to get, because most likely they're not going to agree with your initial demands. And you want to meet somewhere in the middle where both parties feel like they have a win-win situation. So if you know your salary, you know what value you're going to provide to the company, then when perhaps talking about an offer, go into that negotiation and make sure that your initial start is higher than where you might land. That's it for now. Let's talk about an even more exciting topic in the next video, which is what to do if you're lucky enough to get multiple offers. I'll see you in the next one. Bye-bye. Handling multiple offers. This is a great problem to have. If you're able to get multiple offers, well, then you're definitely doing something right. This should be your goal. Your goal going into interviews is not to say, I really hope they hire me. I hope I just get one offer. Ideally, you get multiple offers. The more choices we have, the better we can make a decision on where we should go, where we should work. But first of all, congratulations if you got to this point. Someone finds your skills valuable. But what do you do if you have multiple offers? We know what to do when there's one offer, but what if you have two or more companies interested in you now? You first have to decide which company you want. And you're hopefully handling each of these companies, letting them know that the other has made an offer, and you have figured out what sort of salary and benefits that you're going to get. But salary and benefits aren't the only thing that should matter to you. And over here, I've created a list for you, a priority list of what should go into deciding which company to work for. Number 1 being the most important, and number 5 being the least important, at least in this list. This rank of importance, and keep in mind that this is based on individual situations, should be a guideline for you to decide what company you should go with. The first one is that, is there an offer that you feel you're underqualified for? Is one of the companies offering you a job that you think is way over your head, way harder than the skills that you think you have? Because if that's the case, you should go with that company. You're not taking a job to do the same thing that you already know what to do. You're taking a job to grow and learn so that next time you interview, next time you're looking for a job, you're even better skilled, better prepared, more valuable. So if one of the jobs is way harder than the other, then that's a good sign that you should take it, because that's the one that's going to allow you to really push your skills to the next level. And this relates to the second point, long-term growth potential. Between the two offers, which one allows you to grow? This means not just your skills, being able to become a better engineer, a better programmer, developer, whatever it is you're looking for, but also, is the company growing? Do you have an ability to perhaps grow into that position and get promoted and in better position, better roles. Long-term growth potential. Don't just look at the short term here. So in 5 years, if you stay at this company in 5 years, will you still be doing the same thing? Hopefully not. Third is, will you respect the people you're working with? Are you going to be the smartest person in the room or the dumbest person in the room? Which one do you think is better? If you're the smartest person at a company, well, you're not growing as much, are you? You're not learning from others. You may be in charge and that may be good, but if you're an engineer, developer, programmer, you're looking to improve your skills. If your coworkers, people around you are way smarter than you, that allows you to really grow and learn. And that's a really important factor. The next one, yes, everybody's favorite, salary and benefits. It's pretty surprising that it's number 4, right? But we're thinking long-term here. Salary and benefits aren't as important as the ones on the top in the 1, 2, and 3 spot. And most people put this first, but there's a classic psychological study where they present a cake to some young kids. And they say that you can have this cake now, or if you wait 10 minutes, you can get 2 pieces of cake instead of 1. And they studied immediate gratification versus long-term gratification. And I don't know how accurate the study is, but the point of the study was that the kids who waited for 2 pieces of cake instead of just eating the cake right away and not waiting, the kids who waited were more successful long-term throughout their careers. The idea of delayed gratification, not looking at the immediate benefits, but looking at long-term benefits. Keep in mind that salary doesn't include just money. There's also moving expenses, bonuses, stock options, healthcare, and a whole lot of other packages. So your final decision when it comes to salary and benefits is to combine all of those. Finally, the 5th point is your decision based on desperation? You got to remind yourself, are you doing this because you think you won't get any other offers like this? Because that's not good. You're most likely won't stay at this company for that long of a time, or at least not for your entire life. Most likely, you'll move on to another company in a few years and go through the interview process all over again. So make the decision with that in mind. Is this company worth it? Am I just accepting a job because I'm desperate and I think this is the only option am I going to get? Because if you're going to be in the same position 2 years from now, then that won't really help you, will it? The final decision when it comes to companies is to think about how this will look in the narrative of your life. Will this look good on my resume? If it does, then you should take that job. Don't take the job that's the most comfortable, the easiest, or you're confident that that's the easiest. Take the job that will push you and really stretch and grow you in your career. And at the end of the day, pick the option that will make you happy. If you don't enjoy something, you probably won't be giving it your all anyway. If your job gives you purpose and makes you happy, that's probably a good sign too. And then finally, when you're rejecting an offer from another company, just never burn down bridges. Be nice to people, and you never know when this will come back to help you in the future. I wanted to give you an example of one of my situations when I have multiple offers from each company. I told both companies that I have gotten an offer. I actually managed to get one of the companies to give me an offer after the first company sent the offer and gave me a deadline. So I did exactly like I said in the previous videos, messaged the other company, letting them know that there was an offer on the table. I then had both offers from these companies, and they actually kept increasing the salary because they knew that I was wanted by others. I actually ended up picking the job with a lower salary than the other one because of all these factors that you see here today. And I am here where I am because of that decision. That wasn't the only decision. There's going to be many decisions throughout your life, but really think about the long-term implications. And make sure that you're happy with the decision that you make. I'll see you in the next one. Bye-bye. Welcome back. Let's talk about another fun topic, and that is getting a raise. How do we go about doing this? Getting a raise is hopefully not that hard, because Remember, if somebody hired you, that means they find you valuable. But in order to get a raise, you have to be a good employee. If you're a terrible employee, you don't do your work on time, you don't provide good quality work, then getting a raise is not realistic. So the first step is to actually be a good employee. And hopefully, because you're taking this course, you are the type of person who really values their skills and has a strong self-determined work ethic. I mean, you're teaching yourself how to ace the interviews. You're definitely the type of person who's determined to succeed. So that's a good sign. And when you start a job, you want to hit the ground running. The better you are as the employee, the more likely you are for them to keep you around. And one thing that I really like to do before you start a job is to plan out your career path ahead of time at this company, before your first day on the job. And this should be in the back of your mind throughout your career. This way you have an idea of where you want to be in 1, 2, 3, maybe 5 years at the company. And you can check up on that to make sure that you don't